On the night of July 1st, 2025, the ATLAS telescope at Rio Hurtado, Chile, did what good night watchmen do. It kept scanning for troublemakers. ATLAS, Asteroid Terrestrial Impact Last Alert System, is a NASA-funded survey that sweeps the sky for fast movers that might pose a threat to Earth. Think of it as planetary security, with a very wide-angle badge and an excellent memory for faces. That night, the software noticed a point of light shifting between frames, just enough to shout "moving object," and the pipeline flagged it for human eyes. Within hours, astronomers realized this wasn't just another rock from the neighborhood. Earth is basically a rock that won the cosmic lottery. ATLAS is the bouncer checking who's on the guest list. ATLAS's hardware and cadence are built for speed, short exposures, broad sky coverage, and a nightly loop that lets software measure how a source's position changes from image to image. The pipeline subtracts a reference sky, hunts for residual points, cross-matches anything suspicious, and chains detections into tracklets. If successive positions fit the motion of an object orbiting the Sun, it's business as usual. If they don't, if the apparent motion and brightness don't play nicely with normal solar system speeds and distances, the system raises its digital eyebrow. On July 3rd, those tracklets looked just a little too energetic, and the preliminary orbit solutions wouldn't settle into a neat, closed ellipse. It was the computational equivalent of a bar tab paid with foreign currency. Discovery isn't a single aha, but a relay race. After ATLAS posted the detections, follow-up telescopes piled on to extend the arc. More timestamps mean better math. With each new set of coordinates, orbit fitters recomputed parameters and uncertainties. By the time the Sun rose over Chile, an emerging picture showed a body inbound on a hyperbolic path. Astronomers speak for unbound from the Sun. NASA put it plainly the next day. This thing came from interstellar space. In the cul-de-sac of the solar system, 3IATLAS was the car that never intended to park. The early skyplane motion suggested an approach roughly from the direction of Sagittarius, a busy backdrop near the galactic center that makes discovery harder. Lots of stars, lots of confusion, and plenty of opportunities for false positives. ATLAS cracked it anyway because surveys thrive on repetition and automation. Image, subtract, detect, link, fit, repeat. Once the candidate passed those gauntlets, the Minor Planet Center's clearinghouse role kicked in. Collect follow-ups, refine the orbit, and start talking formal designations. The press translated the math for the rest of us. Third interstellar visitor, moving fast, not a threat, and heading toward a late October 2025 date, with the Sun known as perihelion. Speed is cool, missing Earth is cooler. So why did this particular dot scream "not from around here"? 3 reasons stood out. First, the fit wanted eccentricity greater than 1, the hallmark of a hyperbola, not a bound ellipse. Second, the derived inbound speed at large distance, the excess velocity, wouldn't damp down to something a solar system comet could own. It stayed too high, even after accounting for the Sun's pull. Third, the trajectory didn't line up with any plausible long-period orbit from the distant Oort cloud. Backward integration pointed beyond the Sun's sphere of influence. In short, wrong speed, wrong shape, wrong origin, all delightfully right for Interstellar. Orbital mechanics is cosmic accounting, where every decimal demands receipts, and the receipts agreed. Meanwhile, the observers did what observers do: squeeze photons for every clue. Early images showed a faint coma, evidence that sunlight was already teasing out ices into gas and dust that nudged the classification toward cometary. But with a twist, this one was born under another star's construction codes. Within weeks, bigger facilities swung over. Hubble refined nucleus limits, ground-based teams captured time-lapse sequences. The headlines went from "new moving object" to "third interstellar visitor," and the astronomy Slack channels got very noisy in the happiest way. Astronomy is just group chat with very large cameras. What makes Atlas so good at catching a needle in a star stack is its philosophy. Be everywhere, often, and let the software do the first pass. Humans are great at pattern recognition. Machines are relentless. The moving object pipeline doesn't get bored, and it doesn't blink. It ranks candidates by how well their motion fits a simple model, how consistent their brightness is, and how robust the cross-night linkages are. Most candidates wash out, satellites, glints, cosmic rays, because space photobombs like it's a sport. But when multiple nights of clean detections lock together, and the preliminary orbit keeps refusing a bound solution, the bell rings. If you've ever tried to balance a broom on your palm, you know when it's not going to stabilize. 3IATLAS was that broom, racing off before the trick even began. The human side matters too. Survey pipelines amplify the vigilance of small, distributed teams who live in time zones and coffee cycles, handing off targets as darkness sweeps around the globe. Chile logs it, Hawaii confirms it, Europe models it, social media misinterprets it, rinse and repeat. The difference in 2025 is how quickly the community can pivot from to hyperbolic. Within a day, NASA's planetary defense folks were already shaping public language. No danger, very cool, watch this space. While professionals and amateurs scheduled follow-ups to keep the orbit solution tightening, like a well-tied knot. Clickbait travels faster than light. Sadly, only metaphorically, but solid updates weren't far behind. By the end of that discovery sprint, the object had a name, 3IATLAS, the third eye for Interstellar, and a narrative, a bona fide visitor, barreling through our system on a one-way pass. The Atlas project had done exactly what it was built for: spot fast, coordinate faster, and let physics do the talking. If comets are space freezers, this one arrived with a hint of frost already showing, and a travel itinerary no local could fake. As first chapters go, it's a strong cold open. Next up, we'll strip the jargon off Interstellar itself. What counts as unbound, why eccentricity, larger one is the magic line, and how backward traced orbits prove a rock's passport was stamped in another star's neighborhood. If the solar system is a cul-de-sac, 3I is the car that never intends to park. Interstellar isn't a vibe, it's a verdict delivered by orbital mechanics. The charge sheet has 3 counts: a hyperbolic trajectory, an eccentricity greater than 1, and a past path that, when you run the clock backward, originates from beyond the sun's gravitational reach. Each piece is testable, quantifiable, and about as romantic as a spreadsheet, which is exactly why it works. Start with shape. Bound orbits around the sun are ellipses. An ellipse's how-stretched number is its eccentricity. At the razor's edge, E equals 1 is a perfect parabola, a one-and-done flyby that arrives with just enough energy to escape, like a student who passes the final by 1 point and moves on. A traveler follows one branch in, swings around the sun, and exits along the other, never to return. In other words, hyperbola equals unbound. That's standard celestial mechanics doctrine, not just comic gossip. Shape is only the appetizer. Energy is the entree. The Viviva equation, the orbit world's favorite two-liner, relates an object's speed to its distance from the sun and to the size of its orbit. For elliptic orbits, the semi-major axis A is positive. For hyperbolas, A is negative, which makes the math plainly announce this thing has more than escape energy. Measure the speed at some distance r, plug into Viviva, and if the solution wants a negative A, you're looking at an interstellar drive-by. It's not just semantics, the sign of it encodes fate. Astronomers also talk about hyperbolic excess velocity. V simply, the leftover speed you'd have far away after the sun's pull has faded. If V simply is measurably above 0, you're not bound to our star. Space has no speed traps, but it does have escape tickets. Why does above 0 by a little matter? Because a few homegrown objects have been kicked onto slightly hyperbolic paths after close shoves from giant planets. Those fakes reveal themselves by their tiny VAR barely above parabolic. and by trajectories that trace to a recent planetary encounter. A classic case is comet C1980 E1, flung onto a hyperbola by Jupiter. It'll leave, but it clearly started as a local. For a true interstellar object, you expect a varv-piqué of several kilometers per second, not millimeters over the line, and no recent planetary mugging to explain it. In interstellar terms, born here and just visiting part ways in the second decimal place. There's also a frame of reference wrinkle. We often publish orbits heliocentrically, centered on the Sun, because, well, the Sun is the main act. But for deciding bound versus unbound, professionals move to the solar system's barycentric frame, the true center of mass shared by Sun plus planets, so that Jupiter's heft, for example, isn't quietly biasing the answer. Around perihelion, heliocentric and barycentric elements can disagree in meaningful ways. So the conservative rule is, check the barycentric eccentricity before stamping interstellar on the passport. Precision is the difference between looks hyperbolic today and is hyperbolic in principle. How do we prove a past beyond the Sun's reach? We integrate the orbit backward in time using an n-body model of the solar system. Sun, planets, sometimes the biggest asteroids, plus relativistic tweaks when warranted. But we don't integrate just one orbit, we integrate a family of clones drawn from the measurement uncertainties. Imagine a cone of possibilities widening as you go back. If that entire cone clears the Oort cloud neighborhood and keeps going with non-zero VFin, the object's prior life was interstellar wandering, not a long, lazy loop from our own deep freezer. The elegance here is that the test is statistical, not we think, but the uncertainty volume is outside the Sun's gravitational yard. That's how you swap hunches for confidence. Scientists do love their confidence. None of this requires the object to look special. Interstellar is a kinematic label first, a chemical story second. The pipeline doesn't sniff molecules, it fits positions. Several nights of astrometry, stitched into an arc, let the orbit solver collapse from could be many things to must be hyperbolic. Because small errors amplify over time, early solutions can waver as new measurements arrive. That's why teams keep observing. Each data point shrinks the covariance ellipsoid, nudging E and V towards stable values. When the numbers stop flinching and still shout E larger 1, the champagne can be responsibly opened. Astrometry, the only party where smaller error bars get the loudest cheers. Interstellar also carries a dynamical implication worth spelling out. Gravity will curve the path, but it can't capture the visitor without help. To trap an interstellar object, you'd need a significant energy loss, say a near pass with a planet combined with a braking mechanism like gas drag, which the solar system mostly lacks. In a vacuum playground with few brakes, unbound stays unbound. That's why these objects are scientific lightning strikes. Brilliant, brief, and gone. Finally, there's the public-facing sanity check. When a newcomer is announced, you'll often see 3 simple claims bundled together. It's on a hyperbola, it has hyperbolic excess speed, and it came from outside. On their own, each statement is a hint. Together, they're a proof sketch. Agencies like NASA now summarize this cleanly for general audiences. Closest approach dates, safe distances, and the unbound bit spelled out. Because the best antidote to cosmic rumor is transparent math translated into human. Not every weird sky thing is interstellar. Unusual is cheap. VVin larger. 0 is expensive. So that's the meaning behind the label. Not a poetic flourish, but a mechanical outcome. Hyperbola in shape, excess speed and energy, and a backward path that doesn't boomerang to a long ellipse. Put those together, and you've got a bona fide visitor crossing our cul-de-sac without signaling. Next time, we'll use those tools to compare the third visitor with the first 2. How 1I Oumuamua and 2I Borisov checked the same boxes, yet told wildly different stories. Interstellar visitors, like sequels, same genre, wildly different plots. All 3 share the headline trait of arriving on hyperbolic once-and-done parts, but the similarities mostly stop at from out of town. The fun and the science lives in how differently each behaved under the same solar spotlight. Start with the first act, 3I Oumuamua, 2017. It looked like a faint, star-like speck that stubbornly refused to grow a visible coma. No fuzzy envelope, no tail confetti, just a point and an attitude. As observations piled up, its position didn't match what pure gravity predicted. It was accelerating a smidge, as if something was giving it a gentle push. Normally, that something is gas jets from sublimating ices, but we couldn't catch the usual suspects. No obvious dust, no clear molecular fingerprints. Cue the decade's most polite food fight in planetary science. Explanations ranged from super-volatile outgassing that hides its tracks, to exotic ices, to weirdly porous aggregates that vent efficiently, to mundane comet, but shy. Think of it as cosmic incense you can smell but can't see. Whatever the cause, Oumuamua's defining combo was non-gravitational nudge plus visual restraint, minimal visible activity, paired with undeniable dynamical mischief. Act 2, 3I Borisov, 2019, was the mirror image, textbook comet vibes from the jump. It built a coma, fanned a tail, and paraded through filters like it had read the solar system's etiquette manual. Spectra showed familiar species, cyanogen, carbon chains, water, and friends, while high-resolution images let us watch the coma morphology evolve as it rounded the sun. If Oumuamua was a riddle, Borisov was a field trip. We even tracked its dust-to-gas behavior and noted that its grains skewed toward compactness rather than the fluffier aggregates seen in some local comets. Later in its arc, it hiccuped and shed material, a reminder that nuclei are fragile snow dirt composites, not marble statues. In short, if you'd met Borisov blind, you'd have filed it as ordinary comet, unusual passport stamp. Now enter 3IATLAS. From early days, the photometry and morphology shouted active. A discernible coma and tail, brightness evolution consistent with sublimating ices, and none of the Oumuamua-style cloak and dagger minimalism. In the behavior taxonomy, that plants 3I closer to Borisov, an interstellar that takes sunlight as a cue to vent and shed dust like a comet should. That's a big deal, scientifically, because it doubles our sample of chemistry we can actually measure. It's one thing to infer volatiles from tiny trajectory tweaks. It's much more satisfying to split light and read the barcode of molecules directly. If exocomet chemistry is a cookbook, Borisov gave us a page, and 3I promises a second recipe with new marginalia. Speed-wise, all three arrived with inbound velocities of a few tens of kilometers per second relative to the Sun, fast enough to ignore the welcome mat, not so fast that detectors can't keep up. The difference isn't raw speed, so much as presentation. Oumuamua's geometry left us with a short observational window and brutal phase angles, nudging telescopes into a game of catch it or forget it. Borisov hung around longer at comfortable sun-target-Earth angles, letting amateurs and professionals alike take turns at the eyepiece. Early indications suggest 3I will be cooperative in a Borisov-like way, not leisurely, but not an escape artist either. Astronomers adore cooperative rocks. They're cheaper on coffee. Size is where the trio spread out on the chart. Oumuamua's absolute magnitude implied a small body, tens to perhaps a couple hundred meters along its longest dimension, depending on albedo and shape. And boy, did shape get contentious. Light curve swings hinted at either a highly elongated object or a pancake-like slab tumbling end over end. Either way, small Borisov's nucleus was bigger, sub-kilometer scale, consistent with its robust activity, and the amount of dust released. The eye's early coma makes translating brightness into bare nucleus size trickier. You're never sure how much light is nucleus and how much is the cloud it drags around. But qualitatively, it doesn't look tiny like Oumuamua. If Oumuamua is a compact USB stick, Borisov is a thumb-sized power bank, and 3I seems at least power bank with a case. Astronomy, where about yay big spans an order of magnitude, and everyone nods thoughtfully. Activity is the scientific jackpot, because it unlocks chemistry and grain physics. With Borisov, we measured molecular ratios, compared them to solar system values, and argued about what that mix implied. Birth far from a parent star? A composition skewed by disk temperature? Interstellar tourists carry postcards from the protoplanetary disks that birthed them. 3IATLAS activity means we can extend those comparisons. Look for CO, CO2, water bands, assess how quickly production ramps with solar distance, and test whether the dust scattering behavior points to compact or fluffy grains. Find a pattern across Borisov and 3I, and suddenly one data point becomes a trend. Find a mismatch, and models get better because they must explain diversity. Either way, the universe wins peer review. There's also the story value. Oumuamua forced us to tighten our thinking about non-gravitational forces and detection biases. How many small, low-activity interstellar bodies do we miss because they don't scream comet? Borisov reminded us that the galaxy can produce comets that are comfortably familiar, so familiar that without the hyperbola, you'd never guess its foreign origin. 3IATLAS, by leaning cometry, tells us Borisov wasn't a fluke. That matters for future surveys. When Rubin Observatory turns the sky into a nightly flipbook, we'll catch more of both species, the quiet, pebble-sized minimalists and the hissing snowballs, with tails like punctuation marks. Finally, what each taught us condenses to 3 one-liners. Oumuamua, dynamics can whisper chemistry. Borisov, chemistry can speak for a whole star system. 3IATLAS, the sample size is finally leaving n equals please and entering n equals progress. And yes, the jokes help the math go down. Call it spoonful of sugar dynamics. Next, we'll dissect orbits with a scalpel instead of a sledgehammer. Inclinations, nodes, and why tiny errors can slide perihelion timings in ways your calendar app would envy. Orbital mechanics, cosmic accounting, where every decimal demands receipts. To understand 3IATLAS's path, we need the ledger entries that describe any orbit, inclination, nodes, argument of perihelion, the exact timing of perihelion itself, and then we need to respect how tiny measurement errors can push those numbers around. With interstellar visitors, the path isn't a closed loop. It's a one-pass curve through our neighborhood. Still, the same elements keep score. Start with the headline appointments on the calendar, perihelion and closest approaches. NASA's summary pins 3IATLAS's closest point to the Sun at about 1.4 astronomical units, roughly 210 million kilometers, around October 30, 2025. It will also keep a safe buffer from Earth, never coming closer than about 1.8 AU in mid-December. That's comfortably outside personal space in celestial terms, and it sets expectations for visibility and brightness. Geometry constrains spectacle. Mark the date. The math did. Perihelion, though, isn't just a date. It's a solution to a many-body puzzle. Observers collect timed positions, astrometry. Orbit fitters solve for elements that best explain those positions. Then everyone iterates as new data arrive. Independent pipelines converged on a perihelion on October 29 to 30, 2025, with a distance near 1.356 AU. You'll see slightly different timestamps depending on the dataset and reference frame, but the clustering is tight because the observation arc is now long and the solution stable. Think of it like tuning a guitar string. The early plucks are wobbly. By the end, the pitch locks in. Inclination I tells us how the orbit tilts with respect to the ecliptic, the plane of Earth's path. For 3IATLAS, I is about 175 degrees, which means the comet is on a retrograde track, only 5 degrees off the planetary plane. That's a quirky combo, almost coplanar, but flowing against traffic. Practically, this near coplanarity with a flipped direction shapes which constellations it sweeps through, and how long it stays near the sun in our sky. Short answer, it ducks into low solar elongations around perihelion. For mission designers, that shallow tilt plus retrograde motion also tells you which spacecraft might get a look as it passes the inner system. Elegant chaos. The longitude of the ascending node, where, and the argument of perihelion, where, are the street address of the orbit in 3D. WEC, where the path crosses the ecliptic going north. Where, 128 de Valois, measures how far around the orbit you must travel from that node to reach perihelion. Together with I, these angles orient the hyperbola in space. Imagine rotating a sheet of paper, the orbital plane, and then sliding a pencil mark along its edge to show where the sun's skimming point sits. Once you pin these down, you can predict not just when 3IATLAS is closest to the sun, but where in the sky it will be before and after, and how the tail will project relative to our line of sight. Your planetarium app is basically doing trigonometry in a tuxedo. Outbound path is where the interstellar nature shows its signature. After perihelion, 3IATLAS heads off along the other branch of its hyperbola, with non-zero hyperbolic excess velocity, fading as the inverse square law takes its tax. Because perihelion happens on the far side of the sun from Earth, a tight solar conjunction, the comet is hard to observe at the exact moment of maximum speed, then re-emerges in morning skies as it climbs to larger elongations in November. The big picture is clean. In, swing, out. No capture, no return ticket. While the details, elongation, ecliptic longitude, phase angle, explain why observers get a frustrating lull, right when the physics is spiciest. Now, about those decimals. Every element carries an uncertainty that behaves like a well-mannered but real gremlin. Early in a discovery, uncertainties are big. The orbit family, the set of clone solutions permitted by the data. As nightly astrometry extends the arc, the covariance matrix shrinks and the family narrows. Crucially, the elements are correlated. Nudge the inclination, and Eck and Elbio can shift a little in sympathy, tighten perihelion distance Q by a few thousand kilometers, and the computed perihelion time T can slide by minutes. That's why you'll see slightly different perihelion times reported by MPC-derived solutions versus JPL horizons or community ephemerides. The fits are all defensible snapshots of a moving target in data space. Precision isn't a number, it's a neighborhood. Reference frames add another subtlety. Around perihelion, heliocentric elements can differ from barycentric ones, which reference the solar system's true center of mass. For unbound objects, barycentric parameters are often preferred when you want the infinite future/behavior, because the sun wobbles thanks to the giant planets. Translate between frames carelessly, and you'll invent a phantom shift in eccentricity or timing. The cure is simple: state the frame, propagate the uncertainties, and don't mix apples with slightly heavier apples. Physicists love fruit, they just label it excessively. Measurement systematics can masquerade as celestial drama. A faint, diffuse coma complicates centrating, the act of locating the object's precise center, especially against star-crowded backgrounds near the Milky Way. Sub-arc second biases translate into kilometers of a long-track error a few weeks later, which is why teams aggressively reduce images, cross-calibrate star catalogs, and toss out dubious detections. When a late batch of high-quality positions lands, the solution can jump slightly, cleaning up what looked like a perihelion drift. That's not the comet being fickle. It's the analysis shedding noise. Accountants don't change the revenue, they fix the spreadsheet. Finally, elements are for more than ephemerides. They set up physical inferences. A retrograde near-ecliptic pass means the comet plows through the solar wind and interplanetary dust at unusually high relative speeds and crossing angles, affecting tail morphology and plasma interactions right after perihelion. The precise perihelion distance dictates the thermal load on the nucleus, which in turn sets expectations for activity spikes or fragmentation likelihood, and the outbound asymptote, a direction on the sky defined by I, Ep, and W, tells future telescopes where to hunt as 3IATLAS fades into the dark, taking its secrets and a diminishing photon budget with it. The orbit is the scaffolding. The science gets built on top. Up next, we'll clear a common confusion. 2 Atlas comets, 2 very different family trees. We'll contrast our interstellar 3I with the homegrown C2023 A3 Tsushin-Shan Atlas, so the name tag doesn't trick the plot. Same last name, totally different family reunions. Atlas shows up in both objects' names because the Atlas survey helped find each one, not because they're cousins. One is a once-only interstellar passerby, 3IATLAS. The other, C2023 A3 Tsushin-Shan Atlas, is a long-period comet from our own Oort cloud that made headlines as the so-called Great Comet of 2024. If you've ever mixed up 2 people named Alex in your contacts and texted the wrong one about dinner plans, you already get the problem. Let's start with the passports. Interstellar objects get the prefix I plus a running number. 3IATLAS is literally the 3rd confirmed visitor from beyond the Sun's gravitational jurisdiction. C2023 A3 carries the C tag for a non-periodic comet and a discovery block. A3 indicates the first half of January 2023. The double surname Tsushin-Shan Atlas honors the co-discoverers Purple Mountain Observatory, Tsushin-Shan, in China, and the Atlas Station in South Africa. Same suffix, different story. The naming rules are fussy for a reason. Astronomy is the one field where initials can save you a telescope night. Now the origin stories. 3IATLAS is unbound. Its energy relative to the Sun is positive, so it will swing by once and head back to interstellar space. Psi 2023 A3 is homegrown, a long-period comet that fell inward from the distant Oort cloud, the icy halo surrounding our planetary system. Before it threaded the inner solar system, orbital fits placed its inbound semi-major axis at roughly 100,000 AU, with a perihelion distance of about 0.391 AU in late 2024. In plain English, A3 took the express lane from the deep freeze, dove well inside Earth's orbit, and then slingshotted out again on an extremely elongated track. Interstellar is no return. Oort cloud is CU in many, many millennia. Discovery timelines also separate them cleanly. C2023 A3 was first spotted on 9 January 2023, later pre-covered in 2022 ZD-HEF images, then brightened across 2024, reaching perihelion on 27 September 2024, and peaking for observers in October with impressive dust output and a classic tail. The photographs you saw everywhere, wide greenish comets, elegant dust streamers, were A3s. By contrast, 3IATLAS entered the chat on 1 July 2025, announced promptly by NASA as Interstellar on the basis of its hyperbolic trajectory. If a social feed showed a spectacular 2024 sky scene labeled 3IATLAS, that was a mislabeled A3 glow-up. Internet, we love you. Labels, we need you. Chemistry and behavior. A3 behaved like a very talkative comet. Spectroscopy in mid-2024 showed strong cyanide emission and indications of carbon depletion, plus a hefty dust-to-gas ratio, attributes you can actually measure when a comet throws off molecules and grains with enthusiasm. That activity produced the broad, photogenic tail arcs that made A3 a crowd pleaser. 3I/Atlas, for its part, is active too, an icy body that began showing coma and tail growth as sunlight worked on its surface. But the headline difference is dynamical. It's not coming back. Treat A3 as your exuberant local meteorological event. Treat 3I as a once-in-a-generation road trip through our sky. Orbits and geometry further reduce confusion. A3's perihelion at 0.39 AU put it close to the Sun and, around October 2024, favorably placed for dramatic evening and dawn views from many latitudes. Images from that window October nights with long dust plumes belong to A3. 3IATLAS has its own schedule. Perihelion in late October 2025, much farther out from the Sun than A3's dive, followed by a safe, distant pass relative to Earth in mid-December 20. Even without learning orbital elements, you can separate the narratives by calendar. Spectacular naked-eye chatter. In 2024, that was A3. Interstellar headlines and fresh activity reports in mid to late 2025, that's 3I. Astronomy, come for the math, stay for the date stamps. There's a style difference in the press too. A3 earned the Great Comet of 2024 moniker in multiple outlets after genuinely photogenic displays. The scientific literature now dissects how much dust it shed, how the coma evolved, and what those molecular ratios imply about its birth region in the protoplanetary disk. With 3IATLAS, coverage leans heavily on its status as only the third confirmed interstellar object, with updates focusing on trajectory, excess speed, and the evolving coma as it approaches and departs perihelion. In short, A3's story is bright local comet from the deep. 3I's story is rare visitor with a foreign past. Same genre, different plot lines. Practical rule of thumb for observers and readers alike. Check 3 tags, prefix, year, and discovery partners. If it says 3IATLAS or C 2025 N1 Atlas in earlier notices, you're looking at the 2025 interstellar comet, flagged by the Atlas Chile station and tracked by NASA and the community as an unbound traveler. If it says C 2023 A3 Tuition Sun Atlas, you're in 2024 territory, co-discovered by Purple Mountain and Atlas South Africa, with a perihelion last year inside Mercury's orbital distance. When headlines blur the two, the alphabet soup rescues clarity. Think of the prefixes as airport codes for comets. The itinerary differences are baked right in. One last nuance, Atlas in both names highlights the survey's wide net, not a physical link between the objects. Atlas is designed to sweep the whole sky multiple times a night, catching both neighborhood hazards and rare gems. That it helped tag an Alzut Cloud performer, and an interstellar cameo is a feature, not a coincidence. The cosmos is busy. Atlas just keeps good hours. Next, we'll leave names at the door and talk size estimates for interstellar bodies, how you turn brightness into meters when the subject is wearing a glowing dust cloud, like a misleading jacket. Astronomy, where about yay big, spans kilometers. Ask 5 teams how large 3IATLAS is, and you'll get a polite scatterplot. That's not incompetence. It's physics plus a fluffy coma, doing its best impression of a misleading jacket. Size estimates for active comets are a 3-legged stool, brightness, which includes dust and gas, activity modeling, which guesses how much of the surface is actually venting, and high-resolution imaging, which tries to peel the coma off the nucleus with math, lots of math. First, the headline numbers and why they wobble. NASA's current public summary, anchored by Hubble imaging, reports an upper limit on the nucleus diameter of about 3.5 miles, 5.6 kilometers, with the possibility that it's as small as Himmelblad plants at 440 meters. Upper limit is not a size, it's a boundary. The nucleus must be smaller than this, because even Hubble can't resolve a solid core inside that glow. It's the astronomer's equivalent of saying, the cat is somewhere in this room, then slowly shrinking the room with better data. So why did you also see splashy headlines calling it 7 miles wide, or even 1030 kilometers? Early after discovery, rough brightness to size conversions treated too much of the coma's light as if it were nucleus. Those back-of-the-envelope numbers made for zippy copy, but they were hand-wavy. A later wave of stories leaned on pre-covery images and modeling to claim 11 kilometers, 7 miles. Again, Hubble's sharper view pulled that back by showing the unresolved core must be smaller than the glow suggested. Translation, Media-friendly round numbers travel faster than error bars. In space and in journalism, drag is real. How do professionals turn brightness into diameter when the subject is wrapped in glitter? For inactive bodies, you estimate an absolute magnitude HH. Assume a geometric albedo PP, how reflective the surface is. For active comets, that's a trap. The measured light includes nucleus plus dust gas emission. The fix is to model and subtract the coma. Teams fit the observed profile with a point spread function, PSF, for the unresolved nucleus plus a radial coma term, often Oumuamua Ru or something more elaborate. Convolve with the telescope optics and solve for the brightest nucleus that doesn't overshoot the center pixel. That brightest nucleus maps to the largest allowed diameter, your upper limit. Hubble excels at this game. Its PSF is exquisitely known, which is why its August analysis tightened the size leash dramatically. Brightness isn't the only yardstick. Activity modeling offers a second route. Measure gas production rates, say water, CO2, CO, then ask what active area would be needed, given solar heating, to sustain that outflow. If the required active area is, for example, 0.1 to 1 kilometers squared, you know the nucleus radius cannot be smaller than a pebble. There has to be real estate to host vents. Conversely, if activity looks modest while brightness is high, that hints at dust-rich camene and pushes nucleus sizes down. This is why the early Manhattan-sized quips were risky. They implicitly assumed a bright nucleus rather than a vigorously scattering coma. Comets masters of looking big on camera. A third constraint comes from temporal behavior. If the nucleus were genuinely enormous, you'd expect a certain inertia in how brightness responds to changing sunlight and geometry. Rapid changes, once you correct for viewing angle, can betray that most of the light is thin, quickly evolving dust, not a hulking core. Combine that with color information, how the brightness changes across filters, and you can separate dusty reflectance from gas emission bands, tightening the nucleus estimate another notch. Think of it as forensic accounting for photons. Let's talk errors, the honest kind. 3 big culprits: inflate size, phase function ignorance. We must correct observed brightness for the phase angle, sun, comet, observer. The canonical comet phase function is not a law of nature. Choose the wrong slope, and you'll over or undercorrect the nucleus flux. The large at small phase angle, tiny later illusion has fooled many a newcomer. Albedo assumptions: swap p equals 0.04 to p equals 0.04, classic dark comet, for p equals 0.08 to p equals 0.8, and you halve the inferred size. Since 3IATLAS's surface hasn't been imaged directly, every albedo choice is a guess with consequences. Unresolved coma contamination. Even with Hubble, a tight, centrally concentrated dust spike can masquerade as nucleus light. That's why the most cautious teams report ranges and upper limits, not single hero numbers. Precision without accuracy is just confidence cosplay. Where does that leave us? With bracketed answers, not billboards, Hubble's constraint. La 5.6 kilometers, possibly as small as a few hundred meters, plays referee between exuberant early estimates and sobering PSF fits. Independent write-ups echo that narrowing trend, while popular outlets that touted multi-kilometer diameters often leaned on pre-Hubble photometry or model dependencies that didn't survive sharper images. The safest scientific phrasing today is 3IATLAS's nucleus is currently unresolved. Hubble sets a firm upper limit of 5.6 kilometers, and the true size could be sub-kilometer. That sentence is less fun than Manhattan-sized, but also less wrong. One more sanity check: consistency with dynamics. Extremely large nuclei tend to shed prodigious dust. The coma then becomes optically thick near the center, flattening the radial profile in a way that's hard to hide from space telescopes. Matching the observed profile without invoking a small core plus dust spike becomes contortionist work. This doesn't prove a small nucleus. But it makes the giant iceberg scenario earn every parameter. Why does size matter, besides bragging rights? It sets the stage for survival prospects near perihelion, the surface gravity that controls how easily jets loft dust, and, with density guesses, the mass available to feed the tail. A kilometer-scale traveler tells one story about planet-forming leftovers. A multi-kilometer giant tells another. Either way, we learn how other planetary systems package their debris, and how often such packages wander into our yard. Bottom line, treat single number size claims like you treat suspiciously neat lab data with raised eyebrows. The right mental picture for 3IATLAS today is a nucleus hiding under a bright scarf, definitely smaller than 5.6 kilometers, plausibly much smaller, and waiting for more high-resolution imaging and production rate modeling to tighten the box. Headlines love a clean figure. Science loves a credible interval. Also snacks, but mostly intervals. Next, we'll pivot from how big to what's inside, using spectra and colors to ask whether 3IATLAS is freezer-burned ice, dust-rich crust, or something we haven't tasted before. Comets are space freezers. We're checking what's been in storage for eons. With 3IATLAS, that storage unit came from another star's suburb. So the label maker is unfamiliar, and half the shelves are mysterious. The good news, early color and spectra are already sketching a chemical biography. The better news, the clues are contradictory in the interesting way, like a suspect with two alibis. Start with color, the gateway drug of comet forensics. Near-discovery observations with the NASA Infrared Telescope Facility, IRTF, measured a red optical slope that flattens toward the near-infrared and even goes neutral/weakly blue beyond V1.1 millikins. That's not a standard one-slope-fits-all reflectance profile. The team's takeaway: 3I's dust likely mixes grain sizes and compositions that don't map neatly onto the usual solar system comet libraries. Either an unusual grain size distribution, unfamiliar materials, or both. In short, the crayons in this box aren't our usual 64. Why color matters? Reddening often tracks with small, complex, organic-coated grains. Think irradiation products, aka tholins. While a neutral blue tilt in the NIR can hint at larger, cleaner particles, or even contributions from fine ice grains that scatter differently. That red-to-neutral transition suggests the coma isn't dominated by a single population. It's a cocktail whose recipe changes with distance from the sun and with jet activity. Independent early-season photometry reaches similar color impressions, reinforcing that we're not being fooled by a single quirky dataset. Spectral lines are the smoking guns, and here 3IATLAS is obliging, just not in the copy-paste from a textbook way. In July, IRTF's SPECS instrument delivered the first NI reflectance spectrum and saw no obvious absorption features from exposed water ice in the coma. That doesn't mean there's no H2O at all. It means either A, the water is not abundant in the scattering grains yet, B, the ice particles are too small, warm, contaminated to show the classic 1.5, 2.0 millimeter bands clearly, or C, the line of sight is dust heavy enough to drown out weak ice signatures. It's a familiar puzzle with interstellar seasoning. Meanwhile, a different player lit up carbon dioxide. NASA's SPHERICS mission reported a broad, extended CO2 coma around 3IATLAS, stretching hundreds of thousands of kilometers. Exactly the sort of volatile you expect to sublimate efficiently at heliocentric distances where water is still reluctant. CO2's 4.26 millimeter band is a spheric sweet spot, and seeing a big diffuse envelope tells us the comet's starter fluid is CO2-driven activity rather than H2O. That neatly explains why classic visible band gas emissions tied to water, e.g. karting, the engine that wakes up first, is the dry ice, not the wet stuff. What about the crowd-pleasing green comet effect? That glow usually traces to C2 swan bands in the green and, to a lesser extent, CN near the blue-violet. As 3IATLAS moved sunward, reports of increasing CN emission emerged from co-added optical spectra in early September, evidence that second-stage chemistry is lighting up as temperatures rise and photochemistry in the coma gets to work. That's consistent with many comets. CO/CO2-led activity far out, with CN-C2 switching on as production ramps and parent molecules are cracked by sunlight. Don't treat turning green as a personality change. Think of it as the neon sign on a shop that was always there, now finally plugged in. Tie the threads together and a thermal story emerges. Far from the sun, CO and CO2 are the usual culprits, low-temperature volatiles that vaporize early and push out dust. As 3IATLAS crossed inside a few AU, we'd expect water to join the party, combined with coma chemistry that produces radicals like CN and C2. The current evidence, CO2 already robust, CN flickering on, water ice features elusive Pfitzer comet, whose crust is either crusty, low permeability until warmed, or whose grains are so processed that water stays locked until late. Interstellar weathering helps here. After hundreds of millions of years between stars, cosmic rays and UV-hardened surfaces carbonize organics and conceal pores. Space is a slow cooker with the lid taped down. Dust physics adds more texture, literally. The radial brightness profile from early imaging plus the color slopes imply a mix of compact grains and possibly very fine particles. Compact grains scatter light with a different phase law, how brightness changes with angle, than fluffy aggregates. Add in a pinch of submicron particles, and you can tilt the spectrum neutral in the NIR while keeping the optical red. That's compatible with the complex grain size distribution conclusion from IRTF, and helps explain why simple one-slope color models fail for 3I. If you've ever tried to guess a smoothie recipe by taste, welcome to comet dust spectroscopy. Is any of this weirder than solar system comets? Some commentators leaned hard into anomaly narratives. A useful sanity check, beyond HIM-4AU, most comets are quiet in the visible gas bands because water isn't the driver yet, so the lack of early CNC2 was unsurprising to many comet folks. The genuinely new ingredients are A. How early and how extended the CO2 coma looks for an interstellar object we can monitor from the start, and B. The specific color evolution that hints at grain properties we don't commonly catalog. Call it unusual, not unphysical. The galaxy is big enough to stock several brands of ice. Hubble's teardrop coma imagery bolsters the physical picture without overpromising chemistry. A tidy dust cocoon, a nascent tail, and plenty of unresolved structure near the core, where gas drag shapes grains as they leave. That morphology is what you expect when fresh volatiles are doing the lifting. Clean, directional outflow rather than an amorphous sneeze. It's the lab bench photo to go with the spectrograph readout. So where does that leave the ingredients list? Provisional but exciting. CO2 active coma now. CN joining, water still playing coy, dust grains that blend sizes and possibly host irradiated organics, and surface layers seasoned by interstellar weathering. Think frozen pantry staples with a chef's surprise. As perihelion heat builds, watch for stronger OH, a proxy for water, growth in C2CN, and shifts in color slopes if fine ice grains briefly dominate. If the spectrum sprouts new bands, we'll pin down provenance better. If it stays quirky, we've learned that other planetary systems package their leftovers with different wrappers. Either way, the freezer door is open and the inventory is getting real-time updates. A rare treat for a traveler with no return ticket. Next, we'll follow the physics of turning on the jets, how sunlight flips sublimation switches, why outgassing can ramp non-linearly, and what that means for dust choreography around perihelion. Thermal switch. When space cold becomes space spicy. A quiet, distant comet is basically a sun-powered pressure cooker, waiting for the burner to turn up. As 3IATLAS cruises inward, sunlight ramps from polite to insistent. and buried ices start negotiating with physics about whether to stay solid, become vapor, or erupt dramatically. The result is outgassing, jets of gas that entrain dust, sculpt the coma, and yank on the nucleus with tiny but persistent torques. The catch, the way activity grows, is not a dimmer knob. It's a set of hair trigger switches stacked in series. Start with the simple energy ledger. The surface receives solar power, S time L, slide R2, scaled by heliocentric distance RR, reflects a bit, albedo, radiates some as thermal infrared emissivity, and spends the remainder on sublimation, breaking molecular bonds so solids become gas. If that were the whole story, production rates would scale roughly as R2 R do with a smooth, predictable curve. Real comets, however, laugh at smooth. The vapor pressure of common ices follows the Clausius-Clapeyron relation. P-vap per tolp x-paced L RT. P-vap per tolp x-paced minus L RT, where LL is latent heat and TT is temperature. Translation: a small temperature increase sends vapor pressure and thus gas flux exponential. That's our first non-linearity. Inch the thermostat, the boiler roars. Which ices? Far from the sun, CO and CO2 are the early quitters. They sublimate at lower temperatures. As RR shrinks, H2O joins the party. But the surface isn't a uniform ice tray. Dust mantles, millimeters to centimeters thick, blanket many areas, acting like quilts that limit heat flow and gas escape. Under a mantle, sunlight heats the top, and a sublimation front migrates downward as the thermal wave penetrates. Where pores are open, gas percolates. Where pores are clogged, pressure builds until it punches through a weak spot, making a jet. Cue the second non-linearity, permeability thresholds. Nothing, nothing, nothing. Then a vent forms, and everything happens at once. Comets, the espresso machines of the solar system. The depth the daily heat penetrates is the thermal skin depth, Durham Kp, Pd, Simsroot kappa pp, where kappa is thermal diffusivity and pp is the rotation period. For typical cometary dirt ice mixes, that's centimeters for the diurnal cycle and decimeters for seasonal forcing. Because heat doesn't reach far instantly, peak gas flux lags behind peak sunlight. Thermal inertia, that lag stacks with geometry as the subsolar latitude migrates over a tilted, spinning nucleus. Some regions enter summer, others plunge to winter. The same heliocentric distance can mean wildly different local conditions. That's the third non-linearity, seasons on a potato-shaped snowball. Now add cohesion. Dust grains sit on the surface, held by weak gravity and intergrain forces. Gas drag must exceed a lift-off threshold to loft them. Below threshold, a clean gas jet. Above it, dust storms. Near threshold, metastability. Slight changes in gas production, grain size, or local slope can flip the scene from quiet to confetti. That's why light curves sometimes jump instead of glide. Surface topography weaponizes sunlight. Concavities and pits self-heat as walls reflect infrared back onto the floor, nudging temperatures above what a flat slab would reach. Cliffs can shadow in the morning, then undergo rapid, late-day heating, a thermal whiplash perfect for vent activation. Cavities trap gas. When thin roofs fail, you get outbursts, short-lived brightness spikes, and fans of dust that tell you a door just blew off its hinges. Sometimes the culprit is the amorphous to crystalline transition in water ice, Human 120K and up, which releases latent heat and trapped volatiles. That's a literal phase change booby trap, buried below the surface. Steady warming, then bang, a packet of energy and gas arrives, and jets intensify without any change in the sunlight overhead. Thermal switch, meet chemical spring. Rotation ties the choreography together. A jet is a thrust vector glued to a rotating body. It both accelerates and torques the nucleus. Over days to weeks, outgassing can speed up or slow down the spin, and even reorient the pole, which in turn changes which areas get noon versus dusk sunlight. That feedback loop. Activity alters spin, spin alters insolation, insolation alters activity, can create hysteresis in the light curve. Pre-perihelion and post-perihelion production at the same distance are often unequal because the nucleus has thermally charged and the vents have evolved. Comets keep receipts, just not linear ones. Zoom into a jet. At the mouth of a vent, escaping molecules form a Knudsen layer, transitioning from collisional flow to near ballistic expansion as density drops. The flow collimates along pressure gradients, carrying a preferred direction that can stay coherent for hundreds of kilometers before mixing into the coma. Multiple vents flicker with the day-night cycle, painting rotating spiral fans in time-lapse images. If gas supply chokes, say a vent chokes on its own dust, the jet fades until another crack opens. Think sprinkler, but the lawn is vacuum, and the water keeps changing brand and pressure. Dust return fire matters too. As grains settle, they can blanket once active zones, throttling them, while freshly exposed scarps turn on like neon. The mantle evolves on human timescales, so yesterday's bright jet may be tomorrow's dead chimney. Meanwhile, the gas you thought came only from the nucleus may partly arise from distributed sources, ices that condensed onto grains and later sublimate in the coma, effectively moving the chemistry off surface. That flattens radial brightness profiles and confuses any model that assumes a single, tidy launch pad. Put it all together, and you get why activity ramps are bursty, asymmetric, and delightfully disobedient to straight lines. A small increase in sunlight can cross multiple thresholds at once: permeability, cohesion, phase change, self-heating. The outcome is a choreography of flickering jets, evolving spin, migrating seasons, and light curves that curve for reasons. If this sounds complicated, it is. But that complexity is the point. Each nonlinearity is a clue to subsurface structure and composition you can't excavate any other way. Comets are laboratory beakers, wrapped in cliffs and glitter, and perihelion is when the experiment runs itself. Next, we'll switch from engines to paint, why some comet look verdant and some look bland, and how color stories can trick the eye when the chemistry is busy lying in the dark. Cosmic makeup tutorial: never trust a single filter. When a comet photographs green, it's not because the nucleus is a lime popsicle. The color is a chemistry light show in the gas surrounding the nucleus, the coma, dominated by specific molecules fluorescing in sunlight. The usual headliner is C2, whose swan bands cluster around 510-520 nanometer, right in the green. Add a supporting act from CN, in the violet, near UV, and you get a spectral cocktail that cameras and human brains happily boil down to, whoa, green. The nucleus itself? Typically dark, neutral to slightly reddish, reflecting sunlight like charcoal with a dusting of rust. If you could hold a cometary core under studio lights, it would look more like a parking lot than a traffic light. Here's how the neon switches on. Sunlight pumps certain molecules to excited electronic states. As they relax, they emit light at characteristic wavelengths. Resonance, fluorescence. C2 doesn't usually leave the nucleus intact. It's a daughter species produced in the coma as sunlight photodissociates parents, such as C2H2 or C2H thick, and sometimes more complex organics. CN is similar. Photochemistry liberates it from HCN, or related nitriles, because the parents need time and sunlight to break apart. The green and violet emission is often weak, right at the nucleus, and stronger a little farther out, where there's been enough space and time for chemistry to work. That's why some comets wear a faintly green halo rather than a bright green pinprick at dead center. Now, the instruments. When astronomers say we measured C2, they didn't eyeball a JPEG. They either A, took a spectrum, spreading light into a rainbow and integrating the flux under the swan bands, or B, used narrowband filters tuned to gas emissions, e.g. CN at Hume 388 nanometer, C3 near 405 nanometer, along with continuum filters placed off-band to sample dust-reflected sunlight. Subtract the continuum image from the emission image, and you isolate the gas. It's a little like contouring in cosmetics. One pass for glow, another to subtract the glare. Broadband filters, your usual RGB. Mix everything: dust, gas, and sensor quirks. So color there is only suggestive, not diagnostic. Dust tries to steal the show by being everywhere. Dust reflects sunlight with a spectrum that's roughly solar, but often reddened by particle physics. Small to mid-size grains scatter blue light less efficiently, making the continuum tilt warm. At certain phase angles, the Sun-Comet observer geometry, forward scattering boosts dust brightness dramatically, shifting the overall color warmer even if gas bands are screaming green in a spectrograph. That's how you get two images taken the same night. One photograph looks jade because the processing emphasizes the gas band pass. Another looks golden because it's dust-dominated at a high phase angle. Both can be right and both can mislead if you don't know what you're looking at. Tails complicate the palette. The classic dust tail is sunlight reflected off grains, generally white to yellowish. The ion tail, plasma tail, often trends bluish because of emissions from ions like CO+ and N2+ that radiate in the blue. Then there's the paparazzi rare sodium tail, glowing at the yellow Nair-D lines. It can appear as a razor-thin spear, separate from the dust and ion tails. Meanwhile, that photogenic green lives mostly in the coma, not the tail. C2 and CN emissions are quenched or outcompeted downstream, where densities drop and other processes dominate. So if your friend says, "I saw a green tail," smile kindly and offer coffee. Photochemistry sets scale lengths, typical distances over which parents break and daughters glow. Parent molecules usually decay over tens of thousands of kilometers, while their daughters may emit over comparable or larger scales, depending on sunlight and expansion speed. This is why narrowband images often show gas comae that look broader and smoother than the gritty structures in dust. Dust remembers where it was launched. Jets paint stria in fans. Gas smears itself with molecular indifference. Processing choices can create mythical creatures. White balance routines in consumer cameras, non-linear stretches in image editors, and aggressive gradient removal used to erase light pollution, all tweak color ratios. Stack a night's worth of sub-exposures while the comet moves, and you can unintentionally average a changing spectrum into something that never existed at any one moment. Add the fact that off-the-shelf RGB filters leak a little UV or IR, and suddenly CN's violet contribution bleeds into your blue channel, while C2 pads the green. The result, a picture that's emotionally true and spectroscopically vague. Even professionals must dodge traps. Without a continuum frame, gas images overestimate emissions when dust is bright, without an aperture correction. Bigger apertures capture proportionally more gas than dust, because gas density falls off more slowly. Production rates can be biased. And atmospheric dispersion, the atmosphere acting like a prism at low altitudes, can shift the apparent position of blue and green emissions relative to red, faking color fringes around the coma. Good teams correct for it with an atmospheric dispersion compensator or by observing at higher altitudes. Bad nights have opinions. What about neutral cores? When spacecraft or high-res telescopes scrape away the coma with clever optics and modeling, cometary nuclei present featureless, low-albedo spectra with only gentle slopes, browns and grays, not emeralds. The surface is a crust of devolatilized dust, organics baked by radiation, and sintered ice optically bland in the visible. Any striking color you see in wide-field images is the coma's doing, not the brick at the center. To borrow a terrestrial metaphor, the party lights are fabulous, the venue walls are beige. Assembly age is closer to what we mean by when was the comet made. In most planetary systems, pebbles grow to kilometer bodies within the first few million years, while the gas disk is still around to help. If 3IATLAS formed around another star, odds are it accreted early in that system's youth, call it a few Maya after that star lit up. That alone doesn't prove it's older than our solar system. It just says comets are childhood souvenirs. To beat the sun's birthday, you'd need the parent star to predate ours by tens or hundreds of millions of years, which the galaxy supplies in abundance. Interstellar space is a retirement home for leftovers from many stellar epochs. Dynamical age is the clock that starts when the comet was ejected from its home system. Young planetary systems are chaotic. Growing giant planets fling debris relentlessly. Simulations suggest most ejections happen early, within the first 100 million years, when big planets are still playing gravitational dodgeball. After that kick, an object can drift for hundreds of millions to billions of years through the galactic disk, occasionally perturbed by passing stars, molecular clouds, and the galactic tide. That's why older than the solar system is plausible. A body made, say, 200 million years before our sun, and expelled promptly could have been aimlessly cruising long before Earth existed. Of course, the opposite is also possible. It might be a fresh exile from a very young system, and thus younger than us. Interstellar traffic has no minimum age to merge. Surface age tells a more fickle story. Radiation, cosmic rays, and UV slowly cooks the outer centimeters to meters over Maya timescales, darkening and toughening organics, sealing pores, and creating a processed crust. A single close stellar pass, or one spicy perihelion around any star, can overturn that layer, exposing fresh ice and resetting the clock locally. Even modest activity during this solar flyby will sandblast and redeposit dust, changing the face again. So the surface we see could be ancient, varnished by eons, or fresh, thanks to a recent peel, and different patches can advertise different ages simultaneously. Comet skins are geological mood rings. Thermal age integrates the total heat budget rather than the years. A comet that has made many tight star-skimming passes, even around other suns, carries a deep record of phase changes. Amorphous ice crystallizing, volatiles diffusing, pores collapsing. Another that has spent nearly all its life in deep, cold interstellar space arrives practically cryogenic, with CO2 ready to leap off first, measuring what's missing or abundant, for example, whether super volatile species are depleted relative to water, hints at how much warming has occurred historically. But again, that's a detective's inference, not a clock with ticks. Could isotopes give hard ages? They give context more than dates. Deuterium to hydrogen, DH, in water, reflects formation temperature. Nitrogen and carbon isotope ratios hint at chemical pathways. Oxygen isotopes touch the heritage of the disk's solids. Combined with what we know about galactic chemical evolution, you can say whether the chemistry feels older or younger in a population sense. But pinning an absolute birthday is a stretch. Short-lived radionuclides that make meteorites such great chronometers aren't practical here. Their clocks ran out billions of years ago, and we're not holding a sample in a mass spectrometer anyway. Why not rewind the trajectory and read the timestamp from the sky? Because chaos eats orbits for breakfast. We can integrate 3IATLAS backward for a while in a smooth potential. But tiny uncertainties in its current state, plus gravitational nudges from stars we don't fully catalogue, blow up the error bars within a few million years. After that, any place of origin dissolves into a broad smear on the sky. Galactic dynamics can say it came in roughly from this direction with this excess speed, not it left Alpha Centauri on a Tuesday. The universe keeps detailed accounts. It just redacts names. So when headlines say older than the solar system, the careful translation is the dynamical residence time between stars could be long, and the assembly of the body likely happened early in some star's youth that might precede ours. The better the chemistry matches very cold formation, the more we'll suspect it hails from far out in a disk, regions that most stars build within their first few million years, and the more comfortable we'll be granting it senior status. But there's no single odometer we can read from across space. Age here is a layered concept. Primordial grains mixed with youthful cements, a body assembled in a burst, ejected in planetary adolescence, weathered for ages, and now briefly reheated by our sun before slipping back into anonymity. That layered answer isn't a cop-out, it's the point. Interstellar comets are composite time capsules that let us test how commonplace our own origin story might be, whether 3IATLAS turns out to be a venerable drifter or a recent exile. Every ratio and light curve tightens the story of how disks build ice balls and how galaxies shuffle them. Next, we'll turn the compass outward and ask the hard question behind every age claim. Where did it actually come from? And what, if anything, does its incoming direction whisper about its birthplace? It's the cosmic couch surfer with no forwarding address. When an object like 3IATLAS drops into our neighborhood, the natural impulse is to ask which star to send the "Your parcel arrived" note to. Unfortunately, the galaxy is an expert in witness protection. The best we can do is combine dynamical common sense with kinematic context and accept that birthplace is a probability cloud, not a street address. Start with the big picture. The Milky Way's thin disk is a river of stars and dust flowing around the center, and most of its small debris, comets, pebbles, draft picks for planets, rides along. Young planetary systems are messy. Giant planets migrate, planetesimals pinball, and resonances open trapdoors. In that chaos, a sizable fraction of icy leftovers is ejected. The mechanisms are familiar from our backyard. Scattering by a growing giant planet, secular effects that pump eccentricity, Kozai-Lidov cycles, if there's a distant companion, and in binaries, three-body billiards that don't end with a handshake. Add the fact that many stars are born in clusters, where close stellar passes and tidal nudges are routine, and you have an efficient factory for turning bound comets into interstellar drifters. The galaxy is not short on launch providers. Ejection has a preferred season. Early, during the few million-year window when gas giants form and migrate, damping from gas fades while the gravitational heavyweights sharpen their elbows. That's when planetesimals get either parked in long, stretched orbits or kicked over the fence entirely. The escape speed required at tens of AU is modest compared with what a Jupiter-mass planet can deliver in repeated encounters. Once a body's hyperbolic with respect to its star, it joins the local galactic traffic, moving roughly with the local standard of rest. Think of it as the average stream of thin disk material. Its individual velocity is that stream plus a small peculiar kick from the ejection itself. Net result: when such a traveler wanders into the solar system, its incoming speed relative to the sun is typically a few tens of kilometers per second. Neither a bullet nor a breeze. What then can the incoming direction tell us? First, what it doesn't: a specific star name. By the time an ejected object has roamed for tens to hundreds of millions of years, the spiral dance of the disk differential rotation, epicyclic bobbing, and vertical oscillation has scrambled relative positions. Even if you know the present-day path exquisitely, the phase-space uncertainty balloons backward, and the map of possible birthplaces stretches across dozens of degrees and thousands of parsecs over deep time. Add unmodeled kicks from faint stellar flybys and the occasional brush with a molecular cloud, and the breadcrumb trail dissolves. Galactic dynamics eats linear narratives for breakfast. Still, there are statistical hints. Radiance of interstellar objects tend to cluster relative to the sun's motion through the disk. Because we are plowing into the local stream, more visitors appear from near the solar apex direction, where the sun is headed, than from the opposite. That preference says less about a single birthplace than about membership in the thin disk population, the mundane but important conclusion that these objects are likely drawn from ordinary planetary systems orbiting ordinary stars. If 3IATLAS's radiant and speed sit squarely in that distribution, the simplest story is that it originated around a sun-like star in the disk, not a halo interloper or an exotic hypervelocity source. Boring is beautiful when you're building statistics. Ejection environments imprint subtler signatures, In binaries, for instance, the combined gravity widens the cross-section for flinging debris. Clusters amplify early scattering by adding external tides. Those settings can raise the yield of interstellar comets and skew their velocities a bit higher or lower than single-star systems do. Composition may chime in too. An object rich in CO relative to water likely formed beyond the CO snow line of its birth disk, pointing to colder outer regions. One with depleted supervolatiles could have been warmed repeatedly before ejection, hinting at tighter orbits or later stirring. None of that pins a sky coordinate, but it narrows the type of nursery. Quiet outskirts versus rowdy inner suburbs. Single-star cul-de-sac versus binary roundabout. Could 3IATLAS be a runaway from a known nearby star? That romantic scenario needs 3 stars to align. A radiant that back projects near the star, a relative speed compatible with ejection physics from that system, and an ejection epoch that, when orbits are rewound for both bodies, brings them together with small separation and low uncertainty. In practice, we'd need exquisitely precise 6-dimensional data and stellar past trajectories refined by modern astrometry. Even with that, small uncertainties compound fast. The more time you rewind, the more your cone of possibilities inflates into a blimp. There's also selection bias. Surveys discover what they're optimized to find: certain parts of the sky, certain speeds, certain brightness ranges. That distorts the observed radiant distribution and can make a particular region look special when it's really just where we'd been staring. Future all-sky cadences will help flatten that bias, and when we collect a few dozen interstellar visitors, we'll be able to compare their velocity ellipside, the spread of speeds and directions, to the ambient stellar population. If the match is tight, garden-variety thin disk systems dominate the supply. If we see a hot tail in the speed distribution, perhaps clusters and binaries are overachievers. One speculative but testable angle is time since last bake. If an interstellar object has unusually fresh, fragile volatiles at large distances, that can imply long cold storage without close stellar warm-ups, more consistent with a rapid ejection after formation, followed by eons in the dark. Conversely, chemistry that looks partially cooked could point to multiple earlier passages near a star before the final eviction, more like someone who lived in the inner suburbs and got evicted late. As we build a chemical census across visitors, those patterns may sort sources into cold launch and late eviction families. So the honest answer to where did it come from is a layered shrug with structure. Somewhere in the thin disk, probably expelled by early interactions with giant planets, or a binary, likely formed far from its star if CO2 and CO dominate early activity, and traveling with kinematics that blend a small ejection kick into the local galactic flow. It's the cosmic couch surfer, because the galaxy is one big living room, and most stars own the same sofa set. Trace the fabric and you'll know the brand. Finding the original store receipt is another matter. Next, we'll translate those origins into payoffs, how the debris of distant systems, once freed, turns into testbeds for planet formation models here. What a single interstellar comet can teach us about how worlds grow and what gets left on the cutting room floor. Comets, footnotes from the galaxy's first drafts. A visitor like 3IATLAS doesn't just tell us what it's made of, it pressure tests our ideas about how planetary systems assemble. The trick is to translate coma photons into disk physics, dust, ice budgets, transport routes, and the fine print of how pebbles become worlds. It's less what is this snowball, and more what kind of kitchen wrote this recipe. Start with the dust-ice ratio, the headline number that quietly rules everything from jet vigor to tail texture. In protoplanetary disks, the local dust-to-gas ratio controls whether pebble clumps can trigger the streaming instability and collapse into kilometer-class planetesimals. If 3IATLAS ejects dust copiously relative to gas, that hints its building blocks formed where solids were plentiful and sticky. Pressure bumps near snow lines, dead zone edges, or vortices that hoard grains like cosmic squirrels. A dust-lean coma, by contrast, points to either finer grains that stay trapped in the gas or a nucleus whose surface has been sintered smooth, throttling dust liftoff. Measuring that ratio across heliocentric distances tells us whether the nucleus is a patchwork of reservoirs, some dust-rich, some ice-rich, exactly what you'd expect if it assembled from pebbles born in different disk neighborhoods. Refractory inclusions are the plot twists. If the dust's mid-infrared fingerprints show crystalline silicates, think forsterite olivine peaks, rather than purely amorphous, we're seeing minerals that require high-temperature processing, hundreds to over 1,000 Kelvin, now embedded in an ice ball that formed cold. That juxtaposition screams radial mixing. Hot-baked grains from the inner disk were lofted by disk winds or carried outward by turbulent diffusion, and then locked into icy aggregates beyond the snowlines. Catching a strong crystalline fraction in an interstellar comet would tell us that conveyor belts are not a solar system quirk, but a galactic habit. If instead the spectrum skews amorphous with only faint crystalline signatures, we'd infer a calmer or less efficient transport history. Still instructive because it brackets the range of disks stirring across stars. Ices carry their own cartography. Ratios like CO2H2O and COH2O trace formation temperatures and freeze-out fronts. Co-heavy composition points to condensation beyond the CO snowline, where temperatures are tens of Kelvin. CO2 dominant but water-rich chemistry suggests assembly between the CO and H2O fronts. Water-lean blends might signal prolonged irradiation or multiple warm-ups before ejection. Stack those numbers against exoplanet disk models, and you test whether our canonical temperature profiles and the locations of volatile traps match reality in other systems. Call it snowline truthing with a roaming probe. Organics sharpen the pencil. Methanol, formaldehyde, and nitriles probe grain surface chemistry and UV processing in the natal disk. High methanol relative to water implies efficient hydrogenation on cold grain mantles, which in turn constrains grain residence times and UV flux. If nitriles run hot while hydrocarbons lag, the disk's nitrogen pathways were busy, useful for understanding why some young systems show nitrogen-rich volatiles, and what that might mean for prebiotic inventories on future planets. When you fold isotopes in, DH in water, Beta-15N, DH-14N, in nitriles, Beta-13C, 12C in CO2, you're not just mapping temperature, you're fingerprinting inheritance versus in-disk reprocessing. A DH aligned with very cold chemistry hints at preserved interstellar ices. A moderated DH suggests partial reset in the disk before assembly. Grain physics feeds directly into planet formation. Polarimetry and thermal slopes constrain porosity and size distributions. Fluffy, fractal grains tell us collisions in the source region were gentle. Velocities below fragmentation thresholds, consistent with growth by sticking in pressure traps. Compact. Higher albedo grains imply compaction by sintering or bouncing in slightly more violent settings. Those outcomes calibrate the fragmentation velocity we plug into coagulation codes. In other words, comet dust decides how hard pebbles can bump before dreams of planetesimals fall apart. Chondrule-like inclusions, if any are hinted by composition or mineralogy, would be dynamite. They'd imply exposure to brief high-temperature events, shocks, current sheets, or lightning in a disk otherwise cold. We're unlikely to resolve literal chondrules in a coma, but mineral ratios, Mg/Fe in olivines for instance, and crystallinity levels can triangulate whether grains ever saw flash heating. Find those signatures in 3IATLAS, and disk transient heating becomes a multi-system story, not just solar system folklore. All of this rolls up to the big comparative question: CO and NO budgets. Exoplanet atmospheres are starting to yield these ratios for hot Jupiters and warm Neptunes, and theory links them to where a planet accreted its gas and solids relative to snow lines. Interstellar comets provide the solid phase counterpart. If typical comets from other stars are carbon-rich compared with ours, then planets there might inherit atmospheres with different baseline CO. If the nitrogen budget sits high in ices, you set the stage for ammonia delivery to forming worlds. Suddenly, a faint smudge constrains the grocery list for alien planets. Even the nucleus's internal stratigraphy informs assembly physics. If jets show distinct, stable compositions tied to rotation, that implies layered accretion, pebbles of different provenance glued into strata. If instead, chemistry is homogeneous while dust-ice toggles, the body may have been thermally homogenized or built from well-mixed aggregates. Either way, we tune models of how quickly pebble piles compact, how heat diffuses through porous bodies, and how easily volatiles migrate over geologic time knobs that ultimately decide whether early planetesimals survive to seed planets or crumble into dust. Finally, failure modes teach too. Should 3IATLAS fragment, the exposed interiors would snapshot the unfinished cross-section of a foreign planetesimal, grain sizes, ice pockets, and voids impossible to see otherwise. If it sails through intact but dust-starved, that says surface mantles can choke activity for eons, implying that many interstellar visitors pass unnoticed. A selection effect that matters when we estimate how much solid mass young systems actually eject. The headline isn't, "What did this one comet do?" but which pieces of our planet formation story are universal. Dust ice budgets that enable streaming instability, transport that ferries hot minerals outward, snow lines that set chemistry, and porosities that control mechanical survival. Each has a telltale in a comet's light. Read enough of these footnotes, and the first draft becomes a chapter. Next, we'll follow what happens after the draft leaves home. The slow, relentless edits of interstellar weathering, radiation, sputtering, and time on a body that's been between suns longer than most stars keep the lights on. Deep space, nature's slow cooker, no timer included. Between one star's farewell and another's flyby, an interstellar comet isn't idle. It's marinating in a bath of particle radiation, UV photons, and dust grain hail over millions to billions of years. Those quiet insults rebuild the first few centimeters, sometimes meters of its skin. The result is a surface that looks darker, tougher, and sneakier than the pristine interior, with measurable consequences for brightness, color, and how easily sunlight can flip the activity switch when it finally enters a new planetary system. Start with the omnipresent chisels, galactic cosmic rays, high-energy protons, and heavier nuclei that ignore subtle hints like, "Please don't." They punch through surface layers, rip bonds, and shuffle atoms into new arrangements. In water-rich ices, that means hydrogen gets redistributed and oxygen chains form. In carbon-bearing ices and dust, you gradually build complex, tar-like organics, sometimes called tholins. Each impact is tiny, but the dose adds up. Think of it as molecular woodworking with a hammer, the size of a proton. The optical fallout is predictable. More complex organics tend to absorb blue light efficiently, nudging the reflectance spectrum redder. Over long timescales, though, continued irradiation can cross-link the material so thoroughly that the spectral slope flattens again. Aging makeup that first pops, then goes matte. Color is not a personality trait. It's a mileage sticker. Ultraviolet photons join the party, especially when the comet wanders through regions with bright OB stars or the diffuse interstellar radiation field. UV's job description is simple. Break bonds, liberate radicals, and let chemistry reassemble the pieces into darker stuff. The top microns of ice behave like a chemistry set, with the lid off, peroxides, formaldehyde, and longer carbon chains all take turns. Because UV penetrates less deeply than cosmic rays, you end up with a layered cake, a very thin varnish of photochemistry at the top, then a thicker zone sculpted by penetrating charged particles, and below that, ice and dust that still remember their youth. Sputtering is the quiet sculptor. Energetic ions slam into the surface and knock atoms or molecules clean out of the lattice. Unlike sublimation, sputtering doesn't require heat. It's cold erosion. Given enough time, it shaves away volatiles preferentially and leaves behind a residue of heavier, less easily ejected material. Think dust enrichment by attrition. That residue makes a mantle, a desiccated, mechanically stronger crust with lower permeability. A mantle can smother future activity by choking pathways for gas to escape. Ironically, the same universe that stocked the freezer also shrink-wraps it shut. When outgassing finally begins near a star, the gas must percolate through this crust, building pressure until fissures yield. This is why activity profiles often look jumpy. Permeability isn't a dimmer, it's a trapdoor. Micrometeoroid gardening provides the crunch. The interstellar medium isn't empty. Tiny dust grains zip along at kilometers per second. Each impact microblasts a pit, lofts local debris, and compacts nearby regolith. Over aeons, this zap and tap roughens facets, seals some pores with sintered glassy splatter, and opens others through microfractures. Mechanical properties drift, grain-to-grain contacts weld, porosity reorganizes, and cohesion creeps upward. Gas drag has to work harder later to liberate dust, biasing ejector toward finer particles that can be lifted through tighter throats. Translation for observers: a tendency towards smoother inner coma profiles, and, sometimes, subtler dust features until the crust is catastrophically breached. Electrons and UV also charge surfaces. In sunlight, photoemission kicks electrons free. In plasma, charging depends on the local soup of ions and electrons. In deep space, where sunlight is faint and plasma sparse, equilibrium potentials can still reach values that encourage electrostatic lofting of the tiniest grains on exposed mesas or boulder edges. It's a slow conveyor belt for fines, migrating powder into depressions and leaving pavements of larger, darker aggregates on top. Layer a billion years of that, and you've got a patchwork quilt, ponds of fine dust here, armored plates there, each with its own optical personality when the comet finally brightens. All of these processes edit the albedo downward. Darker surfaces reflect less, so two identically sized nuclei can differ by orders of magnitude in brightness, purely due to weathering history. That's a trap for size estimates that lean on reflected light. Weathering also modifies the phase function, how brightness changes with sun-comet observer angle, because compacted, roughened surfaces and dust populations scatter differently than fluffy, fresh stuff. A seasoned crust can look drab at low phase, but punch above its weight in forward-scattering geometries. The astrophysical equivalent of bad at selfies, great in candid shots. Thermally, the skin evolves from a leaky blanket into an actual blanket. Radiation-induced compaction and sintering raise the effective thermal conductivity modestly, but crucially reduce permeability, so heat penetrates a bit farther while gas finds fewer exits. That shifts sublimation fronts downward, delaying the onset of vigorous outgassing during inbound legs and steepening the eventual ramp once fractures connect to depth. It's the popcorn effect. Kernels with thicker hulls pop later and louder. For a traveler like 3IATLAS, a long interstellar sabbatical practically guarantees some degree of late but lively behavior, as sunshine has to overcome crustal stubbornness before the jets sing. Weathering does not act uniformly. Rotation, shape, and past encounters, even distant, weak ones, create microclimates. Concavities shelter surfaces from sputtering fluxes coming from particular directions. Ridges take the brunt. If the comet ever grazed another star's outer reaches, one hemisphere may have been briefly toasted, resetting that side's clock, while the far side kept aging in the dark. The first days of renewed activity can therefore look lopsided. One jet speaks first, another mumbles through its crust, and a third never manages more than vapor whispers. Observationally, that asymmetry is a clue. not a bug. It's a CT scan of the comet's past abuse. Finally, color trends are expectations, not laws. Some heavily processed surfaces redden, others flatten, and small, fresh exposures can look startlingly neutral against a drab backdrop. Add dust entrained from depth, and you can swing the coma's color temporarily toward the pristine interior. This is why time-resolved color measurements matter. A single snapshot folds weathering and excavation into one ambiguous average. Watch the spectrum evolve as jets cycle and rotation brings new patches into sunlight, and you can separate old skin from fresh cut. The cosmic slow cooker doesn't just season the crust, it rewrites how a comet will perform on stage, how bright it looks when it wakes up, which colors dominate, and how easily it sheds dust. For 3IATLAS, that seasoning is part of the plot, not background noise. Next, we'll turn from surfaces to spreadsheets and show how orbit fitters tame noisy astrometry, propagate uncertainties, and decide when a decimal finally counts as a fact. Measure twice, orbit once. For a comet like 3IATLAS, the elegant hyperbola you see in a press graphic starts life as something far less glamorous, a cloud of dots with timestamps. Turning those dots into a trajectory requires astrometry with milli-arcsecond ambition, timing that knows its leap seconds, and math that keeps its cool when the data have opinions. Begin at the pixel level. Each observatory images the comet against a star field, solves for the plate solution, how pixel coordinates map to the sky, and reports a sky position and time. The accuracy of that step depends on which reference catalog you use. Gaia DR3 is the gold standard, how many stars are in the frame, and whether you accounted for distortions, differential chromatic refraction, and shutter delays. For comets, there's a special gotcha. The center you measure is a photocenter of a fuzzy coma, not the rock itself. A jet or asymmetric inner coma can pull the centroid off by tenths of an arcsecond. Good pipelines model the inner brightness profile or use small adaptive apertures to tame that bias. Great pipelines also flag frames where trailing, poor seeing, or bright background stars sabotage the fit. All those positions and times land in an orbit determination engine that solves a weighted least squares problem. The unknowns are the 6 state vector components, position and velocity at a chosen epoch, and sometimes a few nuisance parameters. The weights encode how much you trust each measurement. A modern fit downweights overexposed frames, trailing limited detections, and sites with known systematics. The result is a best fit orbit and a covariance matrix, a compact summary of uncertainty and the way errors in different elements correlate. That covariance is the difference between a number and a number you can plan around. A quick taxonomy for your next stargazing flex. Green halo equals C2 in the coma. Violet fringe or deep blue inner glow in calibrated data equals CN. Bright yellow needle equals sodium. Long bluish straight tail equals ions. Sweeping tan fan equals dust. If an image screams a single color everywhere, ask what filters were used and how the data were processed. Skepticism is a virtue, especially when photons have traveled millions of kilometers just to be remixed by your photo app. In short, comet color is a spectral conversation between gas emissions and dusty sunlight, heavily moderated by geometry and image processing. Trust spectra and narrowband photometry for truth. Enjoy broadband images for beauty. Up next, we leave the color wheel and step into the furnace, perihelion, the cosmic sauna where comets either glow up or give up. Perihelion, the cosmic sauna where comets either glow up or give up. For an interstellar visitor like 3IATLAS, closest approach to the sun isn't a sightseeing stop. It's a stress test that mashes every system button at once. Heat, pressure, spin, and solar weather. If inbound was a slow simmer, perihelion is the rolling boil. First, the heat, as solar energy spikes. Vapor pressure in near-surface ices rockets upward. Thank you, exponential thermodynamics. and vents that were politely puffing can flip to fire hose mode. Gas drag surges, hauling out dust and carving fans that reshape the coma hour by hour. In parallel, the nucleus endures steep temperature gradients across just tens of centimeters, crust cool at depth, hot veneer at the skin. Those gradients seed thermal stresses that fracture brittle layers and open fresh cracks. For some comets, this is survivable exfoliation. For others, it's the start of a breakup arc. Observations of near-Sun comets show fragmentation consistent with heat-driven cracking around perihelion. Think pottery in a kiln, but the glaze occasionally explodes. If heat is the hammer, torque is the screwdriver. Anisotropic jets act like thrusters glued to a rotating rock, tweaking the spin state. Increase the outgassing at perihelion, and you increase the torque, which can accelerate rotation until centrifugal stresses assist the fractures, sometimes triggering a cascade of mass shedding or full disintegration. This spin-up-to-pieces pathway is increasingly seen as common, especially for smaller nuclei, where a tiny push goes a long way. In extreme cases, outbursts and fragmentation feed back into even stronger torques, a self-reinforcing slide from chunky snowball to debris cloud. Orbital mechanics keep score. Rotational mechanics decides if there's still a player on the field. Brightness behavior near perihelion is dramatic and deceptive. Yes, production rates climb as more real estate passes activation thresholds. But geometry can juice the show. When dust grains pass between us and the sun at very high phase angles, forward scattering can boost apparent brightness by orders of magnitude. That's a lighting trick, not a mass loss miracle. And it's why two comets with similar physics can look wildly different to human eyes. Near-Sun comets can also stage a post-perihelion after-party, in which fresh, fine dust floods the line of sight and makes the object seem to brighten even as it starts to recede. Cameras adore a good scattering angle. Meanwhile, the sun isn't just a heater, it's weather. The comet's plasma environment changes minute by minute under the solar wind and the interplanetary magnetic field, IMF. When a coronal mass ejection, CME, plows through the coma, magnetic field lines can reconfigure and snap, triggering tail disconnection events. The plasma tail detaches and is whisked away while a new tail regrows along the fresh magnetic topology. We've watched this at multiple comets and modeled it end to end. Perihelion season, with stronger solar forcing and a beefier coma, is prime time for dramatic tail surgery. It's as if the comet gets a windsock reset mid-gust. Some of the most photogenic perihelion accessories are specialty tails. Alongside the classic dust fan and the cobalt plasma lance, very bright near-Sun comets can sprout a sodium tail. Atoms kicked off grains or the surface, pushed fiercely by sunlight and glowing at the Nardii lines. Sodium tails are rare to image. The sun's glare is merciless, but when conditions cooperate, they provide a window into grain chemistry right at the source. If you see a razor-thin yellow spear misaligned from the other tails, you're looking at sodium showing off. On the microphysics side, perihelion is when lifetimes shrink. Neutral molecules photodissociate and ionize faster under the boosted solar EUV. The coma's chemical clock ticks quicker. Ion pickup by the solar wind, charge exchange, and electron impact all accelerate, changing the balance of species and the glow of the ion tail. In practical terms, features evolve faster and structures shear sooner. Long exposures compress a lot of chemistry into a single frame. For modelers, perihelion is both nightmare and candy store. Which way does the drama tip, brightening or breaking? History says both, distributed across a zoo of outcomes. Some comets shrug off the heat with a controlled surge in activity and sail through perihelion looking fabulous. Others suffer staged fragmentation. Nucleus splits into pieces, each with its own coma, leading to lumpy light curves and fan-shaped debris clouds. The most fragile simply disintegrate, leaving only a smeared dust trail for dynamicalists to trace. Near-Sun veterans and rookies alike have met all three fates. The deciding variables are nucleus size, porosity, spin state, thermal inertia, and how vents are arranged. Planetary science: come for the equations, stay for the personality tests. Even a survivor can look chaotic. As fresh cliffs collapse and vents choke on their own fallout, the active map redraws itself. Jets wink on where fractures intersect, ices, others die under new blankets of dust. Tail kinematics respond. The dust tail records the recent launch history, curves and striae are jet diaries, while the plasma tail tracks today's solar wind mood. And if a CME passes, prepare to watch a disconnection sprint down the ion tail at hundreds of kilometers per second, a space weather signature legible even in backyard sequences. The comet is both actor and weather vane. For observers, perihelion is less a single moment than a phase with shifting rules. Safety from solar glare determines which instruments can watch. Heliophysics observatories, SOHO, stereo, solar orbiter, can keep eyes on the object as it skims the sun, while ground-based telescopes pick up again when elongation widens. Production proxies like effettery, narrowband gas fluxes, and polarimetry become the heartbeat monitor. A sudden rise without a geometric cause hints at an outburst. A drop with diffuse debris suggests partial breakup. Diagnosing fate means disentangling physics from perspective, and doing it fast, because perihelion is a fast editor. The universe does not wait for your spreadsheet. What should we root for with 3IATLAS? From a science standpoint, survive but misbehave is ideal. Strong activity, evolving jets, perhaps minor shedding, but no total fade to crumbs. That yields chemistry, dust physics, and solar wind interactions in one glorious lab period. But if it does cross a structural threshold and fragment, that too is data. Fresh surfaces, altered torques, and a live view of how fragile interstellar leftovers cope with a star they didn't grow up around. Either outcome teaches space has no sympathy, only information. Next time, we'll swap drama for practicality. When and how to see an interstellar comet with your own gear, what counts as success at the eyepiece, and how to avoid being tricked by the camera's love of flattering angles. Binoculars, because your eyeballs didn't ship with zoom. But let's set expectations. 3IATLAS is a distant, interstellar comet that never comes anywhere near Earth. It's science famous, not spectacle famous. Your strategy is to play geometry, timing, and technique like a pro. First, the calendar. Perihelion lands around October 29 to 30, 2025, at Oumuamua 1.4 AU from the Sun, on the far side of the Sun from Earth. Translation: during late October, it sits in solar glare, effectively in conjunction for ground observers. Expect poor or zero ground-based viewing from roughly early October through the first week of November, because its elongation drops under E. That's the don't roast your retinas interval. Your real window opens after perihelion. As the comet swings out, it re-emerges before dawn in November 2025 at increasing elongations. Through December, it slides across pre-dawn skies, then into darker morning hours by early 2026, as it heads outbound and fades. Nominal closest approach to Earth is still a long way off, about 1.8 AU around December 19, 2025. So don't expect a naked eye show. Think moderate to large telescopes under dark skies. Where to look? Through late September 2025, it lingered in Libra at low evening altitudes, particularly favorable to observers near the equator. After conjunction, it returns to the morning sky, and during December, moves through Virgo toward Leo, while continuing to fade. Plan on low elevation hunts at first light in November, then progressively higher, earlier morning sessions in December, January. Equatorial latitudes again have the edge because the comet's orbit is almost in the ecliptic, but retrograde, Oumuamua 175 declination, keeping it near the planetary plane, but skimming low for many northern-southern sites. How bright? Conservative projections keep it in the 11-14 magnitude regime for much of the accessible window, possibly brighter in stacked images, but visually subtle. In practical terms, 20-25 centimeter, 8 to 10 in apertures with dark skies will be the entry point for visual detection. Once it returns to view, smaller instruments can image it with careful stacking if you track its motion. Treat any comet of the century chatter as the astronomical equivalent of energy drinks. Flashy, not nutritious. Gear that makes a difference. Rancher, binoculars, 10-pec 5A. Great for star hops and framing the field, but likely not enough for the comet itself. Use them to practice the route to your telescope target. Telescope, an 8 to 12-inch Dobsonian, or SCT, with a low-power, wide-field eyepiece, say 25 to 35 millimeter, to pick up the diffuse glow, then step up in magnification cautiously. Higher power can make a faint coma vanish. Filters, broadband light pollution filters, won't conjure comets from the ether. A CN or C2 narrowband helps for imaging gas, but visually the gain is modest. Prioritize darkness over filters. Imaging, a tracking mount plus a cooled camera, lets you stack short subs, 1066, aligned on the comet's motion. Most software supports Comet Stack. Capture a dust-friendly luminance set and a few narrowband frames for CN-C2 if available. Grab a continuum off-band frame for subtraction. Your future self will thank you. Fieldcraft matters more than gear flex. Beat the sun safely. In early November, the comet sits not far from twilight. Do all slews and framing well before sunrise or after full darkness. Never sweep optics near the sun. Use hard stops or a go-to sun avoid setting. If your mount supports it, altitude is destiny. Low elevations mean thicker air and more glow. If the geometry gives you 10 TED at nautical dawn, a hilltop can add precious degrees. Every extra 5 durapulse, dark adaptation and hooding. A simple blackout cloth over your head at the eyepiece can buy you half a magnitude. Old school, high yield. Star Hop Smart. Print or load a comet-specific finder chart for your latitude and date. Generic planetarium views lag. Pull fresh ephemerides from JPL Horizons or a reputable service the day you observe. And class. Expect just a smudge. Diffuse comets hide in plain sight. Use averted vision, gentle sweeping, and compare fields over a 10-15 minute span. Motion is proof you've got it. Planning tools and what they're good for. NASA Science page for one-glance reality checks on date/distances. Is this even visible now? The Sky Live for live positions, rise/set times, and month-by-month visibility notes. Handy when traveling to different latitudes. JPL SBDB Horizons for precise ephemerides at your observing site, including non-sidereal rates for imaging. Sky at Night magazine for timely visibility context, and spacecraft watch notes near perihelion when SOHO, stereo, solar orbiter may spot it, as we can't. Realistic outcomes by month. Quick look, early Nov 2025, reappearance in dawn twilight at low elongation, imaging candidates at low altitude. Visual attempts are advanced mode only. DEC 2025, best ground-based run. Higher elongation before dawn as it crosses Virgo, Leo. Still faint, but reachable with medium-large apertures and longer integrations. Closest to Earth mid-month. Still a very distant 1.8 AU. Jan-Feb 2026. Outbound and fading. Higher, darker mornings, but steadily tougher. Bank your deep stacks now. Your future processing skills will only improve. A few final pro moves. Log sky transparency and SQM readings. 0.3 mag of sky quality can make or break a diffuse target. Bracket exposure times to balance star trailing versus comet trailing, then stack both ways. One stack on stars, one on comet, and blend taste. And label your images 3IATLAS 2025-26 so they're never confused with 2024's C2023 A3 Atlas in your archive or on social feeds. Your captions are part of the science, Bottom line, you can see it, but on its terms, low, dawn side, modestly bright, and exquisitely photogenic to a patient sensor. Treat each clear morning like a small expedition. And remember, even a faint interstellar smudge is a postcard from another sun's backyard. Next up, we'll pan out to the whole observing fleet, from backyard scopes to space-based heliophysics sentinels, and show how the pros coordinate to squeeze every photon for physics. The secret to studying 3IATLAS isn't a single giant eye. It's a relay team that passes photons like batons. Each instrument, from small backyard setups to flagship space telescopes, grabs a slice of the spectrum, a window of time, or a geometry nobody else can. The trick is choreography. Who observes when the comet is low, who watches when it's lost in glare, and who cleans up when it reappears in calmer skies. Astronomy is just group chat with very large cameras. But here, the typing indicator is a scheduling spreadsheet. Start with the scouts on the ground. Modest apertures, say beer, 0.4, 1 meter class at university observatories, and amateurs with 20 to 40 centimeter telescopes excel at cadence. They can watch night after night, measuring the slow pulse of the coma with photometry, catching subtle brightening and flagging outbursts before bigger facilities pivot. Their power isn't raw light, it's persistence. Stack short exposures aligned on the comet's motion, and you get depth. Stack them across many nights, and you get a light curve that means something. When the object sits at low altitude, those smaller domes can pick gaps between clouds that a giant, oversubscribed facility won't waste time on. It's the difference between a city bus and a limousine. One stops more often, and that's the point. Survey telescopes form the wide-angle backbone. Atlas, Pan-STARRS, ZTF, and their kin sweep large swaths of sky, contributing astrometry that keeps the orbit pinned and ephemerides honest. They're not trying to paint a portrait, they're building a time-lapse of where and how bright. Their repeated passes are how we learn if activity ramps smoothly or stutters with outbursts, and their uniform pipelines make cross-night comparisons reliable. As the comet moves away from conjunction and the geometry improves, surveys also catch the evolving tail length and position angle, a sanity check for models that predict how dust should flow given the solar wind and radiation pressure. Measure twice, orbit once. Then you have the specialists, mid-size professional facilities with flexible instruments. A 2.4 mem telescope with a low-resolution spectrograph is a chemistry factory, turning faint light into production rates of CN, C2, C3, and, when the infrared is available, CO and CO2 proxies. Attach an imager with narrowband filters, and you can peel dust from gas by subtracting a continuum frame. Add polarimetry, and you probe grain size and structure, compact versus fluffy, dark versus reflective. This is where it looks green, graduates into C2 column density, does X, while the dust scattering phase function does Y, which is less romantic but infinitely more useful. Flagship ground facilities bring the deep dives. An 8-10 meter class telescope can dissect jets as they rotate with the nucleus, resolve faint shell structures in the inner coma, and grab high signal-to-noise spectra that tease out minor species. Adaptive optics on bright enough inner comatopremy can sharpen features that would otherwise blur into a cotton ball. Because 3IATLAS never gets close to Earth, raw aperture matters. A generous mirror buys you either finer spectral detail at the same exposure time or the same information in weather windows, too short for small telescopes to exploit. Spacecraft step in when the sun becomes both the light source and the enemy. During solar conjunction, heliophysics images do the heavy lifting. SOHO's LASCO coronagraphs can catch the comet as a ghostly thread near the sun, while stereo A views from a different angle, sometimes rescuing days that are unobservable from Earth. Solar orbiters' images have an off-ecliptic perspective that tilts the stage, useful for separating tail components and reading the solar wind's handwriting on the plasma tail. If a coronal mass ejection slams through, these platforms record the ensuing tail disconnect in real time, turning a geometry problem into a physics lesson. Parker Solar Probe isn't built for pretty pictures, but its dust and field instruments can sense the debris and plasma environment in ways cameras can't, adding in-situ texture to the remote views. The sun may hog the spotlight, but the fleet sneaks in from the wings. Once elongation widens post-perihelion, Earth-orbiting observatories take their turns. Hubble's sharp point spread function lets teams strip the inner coma from the unresolved nucleus and push size limits down. It also maps jet fans and inner coma asymmetries that ground seeing smears away. JWST is the chemistry boss. Mid-infrared and near-infrared spectroscopy can identify organics, measure CO2 directly, and probe isotopic ratios if the signal allows, turning a pretty smudge into a compositional dossier. Even if exposure times are costly, a few deep spectra across different heliocentric distances can sketch how the volatile mix evolves, which is exactly the chapter title planetary scientists want to write. Coordinating all this is half logistics, half diplomacy. You need ephemerides accurate to arc seconds for non-sidereal tracking, exposure calculators tuned to a diffuse source, and target of opportunity triggers that play nicely with already booked programs. A small outburst? That's a bat signal to the network. Surveys confirm the magnitude jump. Amateurs post time-lapse. Mid-sized telescopes grab spectra while the gas is fresh. And if timing aligns, a space observatory drops in a narrow window to catch the chemistry spike before it fades. The same sequence plays inverted if a fragmentation event is suspected. Photometry flags the fade. Big telescopes hunt for multiple condensations, and coronagraphs watch how the dust reacts in glare. Data go public fast because an interstellar visitor won't wait for peer review. Preprints and circulars are the currency of the moment. There's also a rhythm to the wavelengths. Optical tells you about radicals and dust scatter. Near IR about organics and water features. Mid IR about CO2 and thermal glow from the grains. Radio can chase OH masers or probe large molecules if you're lucky. Ultraviolet, when available, nails photodissociation products that hide invisible light. Each band is a dialect of the same story. So the most valuable nights are ones that overlap across instruments. Multiplex the sky, and you compress a semester of physics into a weekend. For 3IATLAS, the ideal campaign is a braid. Cadence by small scopes, orbit keeping by surveys, chemistry by spectrographs, glare-proof coverage by heliophysics spacecraft, and deep dive composition by Hubble and JWST when geometry behaves. If that sounds like overkill for a faint fuzzball, remember, this is only the third time the galaxy has mailed us a sample without a return address. We answer by pointing everything we have, precisely and together. Next, we'll zoom into one of those chemistry heavyweights, JWST, and sketch the wish list of molecules and isotopes that could tell us which stellar kitchen baked this particular snowball. JWST, cosmic CSI with better lighting. An interstellar comet is a moving crime scene, and Webb brings the lab spectrometers, images, and a very strict light shielding policy. The goal isn't a pretty portrait, it's a chemical deposition taken under oath. With 3IATLAS, you want to know not just what's there, but how much, where, and in what ratios, because those ratios whisper where and how the object formed. Start with the toolbox. NRSpec is the workhorse for volatile fingerprints between Yim Sip and Bets. It offers 3 main resolving powers: a low-res prism around R100, medium R1000, and high R2700, and, critically, an integral field unit, IFU, that cubes the inner coma. Spatial map plus spectrum at every pixel. That turns fuzzy gas into cartography. Jets versus diffuse glow, gradients with distance from the nucleus, and time-variable hotspots as the nucleus rotates. NICAM's slitless grisms 2.45 mm. Extend coverage with wide fields for brighter comet. Great for capturing broader structures without slit loss hand-wringing. Push past 5 mm and MIRI takes over. Its medium resolution spectrometer, MRS, R150 352T, nails warm dust continua and mid-IR molecular bands that shorter wavelengths can't reach. Together, these three let you interrogate ices, gases, and dust with a consistency you just can't get from a patchwork of ground instruments. The chemistry wish list begins with the usual suspects: H2O, CO2, and CO. Near IR water features, overtone combination bands, are subtle but measurable in sufficiently bright comet. Even when water hides, its photoproduct OH can guide modeling. CO2 is a mid-IR diva at 4.26 mm, and again, in the MIRI regime, often the prime driver when the comet is too cold for water to dominate. CO2's low vibrational lines give you the deep freeze credential, where, in a protoplanetary disk, the ice is likely condensed. The CO2H2O and COH2O ratios aren't trivia. They're thermometers from a star system you'll never visit. Next here, simple organics that sketch the kitchen's spice rack. CH3OH, methanol, CH4, methane, C2H3 ethane, H2CO, formaldehyde, HCN, and its cousins. NIR spec can separate many of these in high-resolution mode, while MIRI catches complementary bands and helps disentangle blends. With a good signal-to-noise cube, you can test whether 3IATLAS looks comet normal by solar system standards or leans toward a composition you'd expect from colder or more irradiated birthplaces. Add mapping, and you can ask whether different jets carry different recipes, localized patches of chemistry that hint at layered geology or uneven processing. Isotopes are the boss fight. DH in water via HDO lines is a keystone for formation temperature and disk history. But it's a faint measurement that demands high resolution, careful modeling, and time on source. If you can pull it off, you get a single number that's worth a paragraph in any Origins paper. Likewise, I-113C/112C in CO2 or organics and Falar 15N, Falar Eintog 14N in HCN are within reach for bright comet and long integrations. Even upper limits prune theories. Interstellar visitors are especially tempting here. Do their isotope ratios sit inside solar system bands, or do they nudge the edges, implying different stellar nurseries or chemical inheritance? Dust matters as much as gas, and MIRI is the dust whisperer. The 10 and 18 mm silicate features trace grain mineralogy, olivines versus pyroxenes, crystalline versus amorphous fractions, and grain-size distributions from the feature shapes and contrasts. A warm dust continuum, combined with NIR color from NIR-CAM/NIR spec, lets you model temperature and size distributions. Are we seeing compact, reflective chips or fluffier IR brighter aggregates? If a fresh jet erupts, repeated MIRI cubes can watch grains cool and settle, turning a tale into a time series of thermal physics. Doing this on a moving target has rules. JWST tracks moving objects well, but the telescope demands a comfortable solar elongation window. That means no observations at true conjunction and a careful pick of post-perihelion slots when 3IATLAS climbs back into the allowed zone. Within those windows, you juggle non-sidereal rates so the comet stays centered, dither patterns to tame detector quirks, and background fields to subtract zodiacal glow cleanly. If mapping near the nucleus benefits from short, repeated integrations to freeze rotation, chemistry is time variable, and averaging can smear the very gradients you care about. Think short scenes, many takes, not single epic shot. There's also the photometric reality check. A diffuse coma doesn't saturate like a point source, but it can fill the slit and inflate backgrounds. The fix is to pair on-comet cubes with off-comet sky frames bracketing the same air mass path. then treat dust continuum and gas lines separately. NIR Spec's low-res prism is a scouting pass. What's there, and roughly how bright, followed by high-res prosecutions on lines of interest. For bright bands, NIR CAM GRISM maps provide context, whether flux spreads, how jets bend, whether a specific species is nucleus proximal or produced in the coma from parent molecules. What would count as a headline from 3IATLAS? A CO2-H2O ratio outside solar system norms, a CO abundance implying very cold formation, a DH that's clearly offset, or spatially distinct chemistry. Say, one jet richer in methanol, while another is CO-loaded, implying a nucleus built from heterogeneous pebbles. Even a null result is powerful. A boringly solar system mix would say that disk chemistry converges on common recipes across stars, strengthening the idea that our pantry isn't special. The big scientific win is synthesis, not a single line. Combine NI-Spec's volatile grids with MIRI's dust mineralogy and NICAM's spatial context, and you get a story that connects disk temperature, irradiation history, and aggregation pathways. For an interstellar comet, that story is a postcard from someone else's protoplanetary neighborhood, delivered once, read carefully, then gone for good. Next, we'll step out of the lab and into deep time, asking how old such a traveler might be and what age even means when a snowball has spent eons drifting between stars. If rocks could brag, this one's flexing seniority. But how old is 3IATLAS hides a trick question. Because comets wear multiple calendars at once. There's the material age, when the atoms and grains formed, the assembly age, when those grains got glued into a comet, the dynamical age, how long it has wandered unbound between stars, the surface age, time since the outer layer was last reset by heating or erosion, and the thermal age, how much cumulative baking it has endured. Ask a single number and you'll get a committee. Start with material age. Many comet grains are a mashup, presolar dust, older than the sun, mixed with silicates that condensed in a protoplanetary disk. Some bits can be literally ancient. Microscopic presolar grains formed in prior generations of stars. Others crystallized right before the comet assembled. If you could pluck a particle from 3IATLAS, you might find isotopic quirks that scream born in a different nursery, but that still wouldn't timestamp the whole comet. Material age is like counting the bricks to date the house. It tells you the quarry's story, more than the move-in date. Least squares is only the first pass. Teams generate Monte Carlo clones, thousands of orbits sampled from the covariance, and propagate them to map not just the mean path, but the full probability distribution. That clone cloud tells you how confident you can be about, say, the exact hour the comet slips into a chronograph's field, or whether a close approach to a planet will be nominal or geometry tweaked by a few thousand kilometers. For a hyperbolic visitor, even a small uncertainty in excess speed or direction can shift the perihelion time by minutes to hours. Most nights that's trivia. Near conjunction, where observing windows are razor thin, those minutes are the difference between in the frame and just missed. Outliers deserve a courtroom. Orbit fitters inspect observed minus computed residuals OC as a function of time, observatory, air mass, and seeing. Patterns say a particular site always off to the northeast by 0.4 suggest a catalog or reduction bias. Those data get reweighted or rejected. Automatic sigma clipping is useful, but smart clipping is better. You don't want to toss genuine dynamical behavior as noise. For comets, that includes the possibility of non-gravitational accelerations from jets. When residuals show a coherent trend with heliocentric distance, fitters add the standard A1, A2, A3 parameters, radial, transverse, normal accelerations, scaled by a sublimation law. If they matter, residuals calm down. If they don't, the fit refuses the complication. Occam writes orbits, too. Timing is a quiet saboteur. Mid-exposure times must be in a uniform scale, usually TdB, and corrected for shutter travel and readout. A 1-second timestamp error at comet-like angular rates can be milli-arc seconds of position. Trivial on one night, cumulative over weeks. Likewise, light time is baked into the computation. You observe where the comet was when the photons left. For fast movers, using the wrong iteration level for light time can leave a fingerprint in the residuals that looks like a physics problem, but is really a bookkeeping one. Orbital mechanics may be grand, but it's built on pedantry. Astrometry doesn't happen in a vacuum. Ironically, backgrounds change. Near the Milky Way, crowded fields induce confusion. Near bright stars, scattered light bends centroids. At low elevation, refraction elongates the PSF and introduces color terms. Fitters track these contexts and often impose sight flaws. Even if a formal uncertainty says 0.05 inch, the data from that configuration get a 0.3 film minimum because life is messy. The weights reflect reality, not optimism. What does all this mean for visibility forecasts? First, magnitude predictions inherit orbit uncertainty through geometry. If your position uncertainty changes the expected phase angle by a degree or two on a given morning, your brightness estimate can slide by tenths of a magnitude, enough to flip a maybe into a nope for small telescopes. Second, tail orientation predictions, used to plan narrowband imaging or polarimetry, depend on precise skyplane motion. A shifted path can rotate the tail's position angle by several degrees, complicating comparisons across nights. Third, spacecraft windows are merciless. A coronagraph's occulting disk or a detector's vignette doesn't care that your ephemeris was almost right. Adding new data is like tightening a knot. Each fresh night shrinks the covariance, but not uniformly. Some directions, a long track, collapse faster than others, cross-track. Early follow-up that extends the time baseline is worth more than a heap of same-night points. Variety beats volume. That's why coordination matters. A handful of well-timed observations from widely separated longitudes or hemispheres can reduce uncertainty far more efficiently than dozens of redundant measurements from one place. Finally, communication closes the loop. Orbit solutions aren't scripture, they're living documents. When a pipeline posts an updated solution, observers should pull fresh ephemerides before heading out, and images should record exact timing and pointing, so their frames remain scientifically useful, even if the target was faint. The best campaigns run on a steady rhythm: observe, fit, propagate, post, repeat. The decimals won't thank you, but your signal to noise will. We've now built the map and learned how to trust it with error bars. Next, we'll step outside the spreadsheet and into the feed, separating sober dynamics from splashy narratives. What's real, what's rumor, and how to inoculate yourself against viral space nonsense. Clickbait travels faster than light. Sadly, only metaphorically. When an interstellar comet like 3IATLAS makes headlines, the internet flips straight to the season finale, impact rumors, never-before-seen chemistry, and graphics that look like disaster movie posters. Let's build a nonsense firewall. What the words actually mean, what data to check, and how to spot a post that's running on vibes instead of physics. Start with the biggest myth. It's headed for Earth. No, its trajectory is unbound, which is what interstellar means in this context. The path is a hyperbola, not a closed loop. So it's in, around the sun once, and out. Headed for Earth would require the orbit to intersect our planet's position at the same time. Geometry is picky like that. The go-to sanity check is the closest approach distance. If the number is in astronomical units, AU, greater than Enum 0.05, that's millions of kilometers, cosmically near, emotionally far. For 3IATLAS, the missed distance stays huge. It's a data-supported shrug, not a cliffhanger. Myth 2. Interstellar equals unprecedented danger. Interstellar is a kinematic label, not a hazard rating. It means the object's eccentricity exceeds 1, and it carries hyperbolic excess speed. enough energy to escape the sun. None of that implies a collision course. A flyby with extra pep is still a flyby. If anyone implies otherwise, they've confused energy with aim. Myth 3. Size inflation. You'll see city-sized, Manhattan-sized, and occasionally continent-adjacent. Active comets surround themselves with glowing dust and gas. Brightness is not body. Professionals report upper limits when the nucleus can't be resolved and give ranges when modeling depends on assumptions like albedo and dust contamination. When a headline offers a single, very round number, look for the fine print that isn't there. Myth 4. The tail as an arrow. A tail does not point along the direction of motion. The dust tail roughly traces the recent path plus radiation pressure effects, and the ion tail points away from the sun along magnetic field lines carried by the solar wind. If you see a graphic with the tail leading the comet, like a spearhead toward Earth, consider it modern art. Myth 5. It turned green, so chemistry changed dramatically overnight. Green glow may usually come from C2 fluorescence, often amplified by image processing. The timing of that glow depends on sunlight, photochemistry, and geometry. A new photo doesn't necessarily mark a compositional plot twist. Trust spectra and narrowband photometry, not a single heavily stretched JPEG. Myth 6. Astronomers are hiding the real orbit. Orbits are public homework. Positions and times go to clearinghouses. Fits get updated as new data arrive. Uncertainties shrink. Perihelion timings and visibility forecasts adjust by minutes to hours. If you watch the numbers move and call that suspicious, you've mistaken error bars tightening for conspiracy. Science is a version-controlled document on purpose. Now the practical toolkit for myth-proofing. Check the source and chain. Who first reported the claim? Trust primary outlets, a mission's official page, JPL ephemerides, observatory press rooms, or peer-reviewed preprints by teams you can name. A repost of a repost with a meme font is not provenance. Look for numbers with units. Distance in AU, timestamps in UTC, brightness in magnitudes, and orbital elements with uncertainties are green flags. Vague phrasing, closer than ever, brighter than the moon, is a red one. Verify the geometry. A quick ephemeris check tells you elongation, angle from the sun, and expected altitude before dawn or after dusk. If an article shows a majestic evening panorama, while the elongation is 18 degrees at civil twilight, the photo is either archival or aspirational. Magnitude reality. The astronomical magnitude scale is logarithmic. A change of 5 magnitudes is a factor of 100 in brightness. If someone forecasts a jump of 7 magnitudes overnight without an outburst mechanism, they're promising a unicorn. Expect gradual ramps, plus occasional spikes with physical triggers, fractures, outbursts, not daily yo-yos. Image hygiene. Reverse search the viral image. You'll often find it's a classic comet shot with new captions. Also, watch for oversaturated colors and non-linear stretches that turn faint gas glows into neon signage. Pretty is fine. Pretty isn't proof. Language tells. Phrases like NASA confirms impact, astronomers stunned, or they don't want you to see this are copywriter catnip. Scientists prefer consistent with, we infer, and uncertainty remains. Boring tone, trustworthy content. Context, not cherry picks. A single measurement out of family isn't a twist ending, it's a candidate for re-reduction. Patterns across multiple nights, telescopes and teams carry the weight. If a post leans on one uncorroborated frame, treat it like a plot hole. Know what can change. Early orbits wobble. Photometry during low elongation is messy. Non-gravitational forces can tweak timing. Those aren't loopholes. They're the known moving parts. Predicting to the minute weeks ahead is theater. Expect updates, not reversals of physics. Beware unit salad. Mixing kilometers, miles, AU, and football fields in the same paragraph is a tell that precision isn't the priority. If they won't pick a system, don't pick their conclusion. Ask what's falsifiable. A concrete claim, closest approach on deck X at YAU, can be checked. A vibes claim, biggest ever seen by humankind, evaporates under even a modest comparison to catalogued comets. If it can't lose, it isn't science. Finally, don't confuse underwhelm with undervalue. Most interstellar comets are not naked eye spectacles. They're information-dense smudges that let us test how other solar systems build ice and rock. If the night sky doesn't deliver fireworks, your camera and the data do. The real plot is in ratios, light curves, and spectra that will outlive a week of headlines. In short, check the missed distance, decode interstellar correctly, anchor on primary numbers, and let uncertainty be a feature, not a flaw. Skepticism isn't cynicism, it's quality control for wonder. Next up, we'll take that sense of proportion and aim it at an irresistibly impractical question. Could we chase a visitor like this? And sketch the sprint-level engineering that makes mission daydreams both tantalizing and brutally hard. Space missions build times that make sourdough look fast. The minute an interstellar visitor gets announced, every engineer's whiteboard fills with arrows, Del V budgets, and the faint smell of optimism. Could we actually chase 3IATLAS or its future cousins and grab close-up data? The honest answer is maybe as a flyby. If you've planned for years, probably not as a rendezvous, unless you've bent physics or the calendar. Still, daydreams make good blueprints, and a few are almost practical. A rapid response flyby starts with time, the one resource rockets can't launch. You need detection early enough to pencil an intercept trajectory that the launch vehicle can realistically supply. That means tens of months, not tens of days. Survey first, debate later. Even for a modest intercept, your hyperbolic target is sprinting through the inner solar system at many tens of kilometers per second. To touch it, you either leave Earth screaming fast, high C3, or you leave early and let celestial mechanics do some of the work. Spoiler, building an interplanetary craft and its ground segment in under a year makes even caffeine nervous. One clever hack is pre-positioning. Park a small interceptor at the Sun-Earth L2 point, powered and waiting like a sprinter in the blocks. Give it efficient solar electric propulsion, Hall thrusters sipping xenon, and enough propellant margin to pounce when a target appears. When a new interstellar is flagged, the spacecraft drops from L2, spirals onto an escape trajectory, and tweaks toward the predicted crossing point. The upside is responsiveness. The downside is lifetime and patience. You might wait years before the right candidate appears, while electronics age and team funding auditions for patience awards. Also, electric propulsion trades time for Del V. If the intercept geometry demands brutality, a chemical kick stage may still be needed. Another approach borrows from the Oberfurth playbook: go deep toward the sun, burn hard where your speed is highest, and hurl yourself onto a high-energy intercept. That needs a heat shield with Parker solar probe swagger and a solid or cryogenic stage willing to fire near perihelion. It's technically delicious and operationally terrifying. Thermal margins get thin. Guidance must be perfect. And if you're staging hiccups, you've built an extremely expensive marshmallow roaster. It's the kind of maneuver proposal that makes review boards reach for stress balls. Gravity assists sound romantic. We'll slingshot around Venus, then Earth, then Jupiter. But assists cost calendar. A Vega chain takes years, and interstellar targets are on semester time. By the time you've lined up the planets, your quarry has signed your yearbook and left. Gravity is generous with velocity, stingy with schedules. Nuclear electric daydreams are perennial because they promise both high ISPA and real thrust. A compact fission system, powering multi-kilowatt electric thrusters, could spin up the Del V you need without a touch-the-sun stunt. But nuclear space power isn't an off-the-shelf item. Regulatory, launch, and development timelines are measured in political cycles. When the target's clock is ticking in months, awaiting reactor qualification is not a mission phase. It's a punchline. Okay, say you do get there. What's on the bus? at flyby velocities of 30-80 kilometers less, even more if you rode the Oberth roller coaster. You trade intimacy for instance. You want a narrow-angle camera with absurdly fast exposures and a wide-angle context imager to catch jets and the tail. Add a dust analyzer with a sacrificial Whipple shield up front, a compact mass spectrometer to sniff volatiles in the coma, a magnetometer on a boom for the plasma environment, and maybe a UV spectrograph if geometry isn't cruel. Navigation is optical. Track the target against stars, predict its apparent motion hours ahead, and let an autonomous guidance loop keep the nucleus pinned during closest approach, because Earth can't joystick millisecond decisions from light minutes away. Shielding isn't optional. A single sand grain at 50 kilometers s is a bullet that majored in overachieving. The spacecraft rides behind layered shields. High-risk instruments peak only during the seconds that matter. Even then, you pick approach geometry carefully. Coming down the tail lowers dust fluence. Across tail pass buys chemistry with fewer dents. Trade studies look like culinary recipes. Remove 200 meters of risk with 1 dB of shield mass. Garnish with attitude constraints. Data is the cruelest constraint. Closest approach is a blink, minutes of high-value frames and spectra, and downlink happens later, at leisure, after you've left the danger zone. You pre-script the encounter timeline like a stage play with no second act. Instrument modes, gimbals, exposure ladders, compression strategies, all frozen weeks ahead. If the nucleus fragments mid-approach, you rely on a thin layer of autonomy to widen exposure bracketing or shift aim points. No do-overs is printed on every checklist. Could a swarm help? Absolutely. A carrier bus could release a handful of CubeSats hours before intercept, each tasked with a single measurement, plasma, dust, imaging, so that loss of one isn't a mission ender. They'd radio data back to the carrier for later downlink, spreading risk and sampling multiple altitudes. The price is complexity. More radios, more navigation, more simulations for dust survival. Complexity has a gravity field of its own, so why try? Because even a fast flyby returns disproportionate value. A resolved view of an interstellar nucleus, a mass spectrum of its gas and dust, in situ plasma data, as the solar wind tangles with alien volatiles. Those are first you can't fake from Earth. And a ready-to-pounce architecture isn't just for interstellars. It helps with weird comets, outbursts, and new small bodies we'll start catching nightly as surveys accelerate. Build once, use often, sleep better. What makes it tough is a three-headed hydra. Lead time, energy, risk. You can blunt the first with pre-positioned hardware, the second with clever maneuvers and/or better propulsion, and the third with shielding and autonomy. None removes the fundamental truth. Space is big, fast is hard, and calendars are cruel. But if the plan is be there when the galaxy drops by, you don't argue with the doorbell, you keep your shoes by the door. Next, we'll pivot from rockets to particles and hairdryers, the sun's steady breath, and the dust it tosses, unpacking how tails grow, bend, and occasionally misbehave when the solar wind decides to restyle a comet's look in real time. The sun blows a constant hairdryer. Comets oblige with dramatic hairstyles. Give an icy nucleus sunlight, and it exhales a cloud of neutral gas that drags dust with it, building a coma, think atmosphere in training, expanding at a few hundred meters per second. Close in, collisions between molecules smooth that cloud into a roughly spherical glow. Farther out, the gas thins, chemistry kicks in, and sunlight starts breaking parents into daughters. That neutral coma is the raw material for everything stylish that follows. The dust tail sculpted by sunlight's shove, and the plasma tail carved by the solar wind's magnetic mood. Dust is the low drama, high aesthetics half. Grains leave the inner coma with the gas. Then each feels two main tugs, solar gravity inward and radiation pressure outward. Their ratio is bed. Small, light grains have big bed and get flung more forcefully, while larger pebbles loaf along with Ben Itsirin 0 point. The result is a tail that is broad and curved, with gentle parabolas that sort grains by size. Draw the math and you get the classic Finson-Probstein picture. Syndines, constant bet, and synchrons, constant release time, weaving a map of arcs. Observationally, that means the tail's shape remembers both what sizes were launched and when. If the comet coughs an outburst, the synchrons light up, and you can read a timestamp right off the curvature. Grain physics is a historian. Sunlight is the archivist. The plasma tail is the drama magnet. Once neutral molecules are ionized by UV photons or electron impact, they join the solar wind's game. The interplanetary magnetic field, IMF, frozen into the wind, drapes around the coma like streamers around a lamppost. Newly made ions feel the electric field of the moving plasma, formally, and are swept anti-sunward along the field, making the thin blue ion tail that often points almost exactly away from the sun. Mass loading, dumping tons of slow ions into a fast wind, slows and deflects the flow, building a cometary plasma environment, bow-like disturbances up front, a contact surface separating solar and cometary plasmas, and in strong outflow, a diamagnetic cavity near the nucleus where the magnetic field is pushed out entirely. It's a magnetosphere, but brand new and made fresh daily. Near perihelion, the lab turns on all the knobs. Gas production surges, so the radius of the collisional inner coma swells, and the plasma boundaries balloon outward, sometimes by orders of magnitude. Ionization times drop with the rising ultraviolet flux. Within minutes to hours, the neutral outflow is converted into a river of pickup ions that spiral along B. The draped field lines tighten, current sheets sharpen, and the ion tail narrows into a high-contrast lance with fine structure rays, kinks, and rapid wiggles that trace the passing of alphenic disturbances. If you ever wanted to diagnose a plasma with nothing but a long exposure photo, this is your playground. Mass loading doesn't just slow the wind, it changes the math. The added ion population modifies local alphen speeds, alters the effective Reynolds number of the flow, and creates conditions ripe for instabilities. Kelvin-Helmholtz waves can ruffle the boundary where cometary and solar wind plasmas slide past each other. Tearing modes can nibble at thin current sheets in the tail, seeding patchy reconnection far downstream. In images, that physics appears as braided filaments or sudden bends, often evolving on tens of minute timescales. The wind is invisible, the tail is its ink. Dust and plasma choreography share the same stage but different tempos. Dust responds to sunlight and inertia. It remembers the last days to weeks. Plasma responds to hour-by-hour space weather and forgets fast. That's why you can see a serene, sweeping dust fan underlaid with a jittery, needled ion tail pointing a different way. Add perspective, large phase angles that enhance forward scattering, and the dust can look briefly brighter than physics changed, while the ion tail, indifferent to our lighting tricks, keeps telling the wind's story. Two actors, one spotlight, separate scripts. Perihelion proximity sweetens subtleties. The phase angle grows, so grains that are normally wallflowers flare in forward scatter, revealing stria, combed streaks that trace quasi-periodic jetting from rotating vents. Those same vents, when projected into the plasma, imprint spiral brightness patterns in the inner ion tail, as local ionization rises and falls with the day-night cycle. Meanwhile, the solar wind's own weather sector boundaries, where the IMF flips polarity, shocks and sheaths from upstream disturbances, sweeps through, shifting the draping angle and compressing the tail. You can watch a comet's private magnetosphere breathe in sync with a star 150 million kilometers away. Long-distance relationship, excellent communication. The inner transition from neutral to plasma is a work of microphysics with macro consequences. Photoionization, electron impact ionization, and charge exchange set the pace. Each species, H2O, CO2, CO2, CO feeds ions with different masses and reaction cross-sections. Pickup ions begin as ring distributions in velocity space around the magnetic field and relax toward broader beams via waves they themselves generate. Those wave-particle interactions can then scatter electrons, boosting electron impact ionization, closing a feedback loop that brightens the inner ion tail. A comet makes its own radio noise. The tail is a self-written plasma textbook. Even the direction of motion sneaks into the look, because radiation pressure slackens with distance, while gravity doesn't. Dust released before perihelion curves differently from dust released after. That gives post-perihelion tails a subtly different silhouette, even at the same heliocentric distance. The ion tail, however, doesn't care where the nucleus is headed, only where the sun is and how B is leaning. If the two tails seem to argue about where to point, they're not fighting, they're answering different questions. For modelers, near-perihelion campaigns are candy. Fit the dust with Syndine synchrone grids and retrieve grain sizes and launch times. Fit the ion tail with MHD or hybrid codes and retrieve mass loading rates, field draping angles, and the location of the cavity boundary. Cross-check against gas production from spectra, and you close budgets: how many molecules became ions, how strongly the wind was slowed, how far the comet's mini-magnetosphere pushed back. It's rare to see so much plasma physics in pure silhouette. All that hairdressing fades with distance. As outgassing ebbs, the cavity collapses, ionization slackens, the plasma tail thins to a whisper, and dust grains disperse into a pale fan that gradually aligns with the orbit as the smallest particles are blown away. The comet tucks its hair back under a hood and keeps walking. Next, we'll follow that walk into the dark, how 3IATLAS exits the stage, how quickly it fades below our reach, and what its outgoing trajectory tells us about the long goodbye of an interstellar visitor. It Irish goodbyes the solar system at interstellar speeds. Once 3IATLAS rounds the sun and the glare loosens its grip, the visitor doesn't hang around for small talk. It follows the outbound branch of its hyperbola. The same energy it carried in now simply pointed the other way. In the barycentric ledger, its hyperbolic excess speed is essentially unchanged. Gravity bends the path, not the personality. The asymptote fixes a one-way heading into the galactic traffic, a lane choice encoded by the orbit's inclination, node, and argument of perihelion. From our vantage, that translates into a gradual swing to higher elongations as dawn recovers the comet from conjunction, then a steady drift into darker sky and thinner signal. Interstellar is a kinematic promise kept. Once past the warmest road, it's all distance and diminishing returns. The brightness decline has a double tax. Photons fall off with both heliocentric distance, the sunlight that powers the show, and geocentric distance, how far the smudge is from us. For a dust-active comet, visual magnitude roughly follows something like Ra n Dalv Tether 2, with n often steeper than 2, because sublimation throttles back as insolation wanes. In plain terms, the energy force it closes, the coma thins, and the same handful of grains must shine from farther away. Add phase angle effects, forward scattering magic near the sun that vanishes as geometry relaxes, and the descent can feel abrupt. A week after perihelion, the object may look feisty in a coronagraph. A month later, you're chasing it with long integrations and averted vision. By early in the new year, you're arguing with the background. Instruments say their farewells in shifts. Near the sun, heliophysics images catch a last cameo, a thin line in a coronagraph's field for a day or two. Ion tail nervously sketching the solar wind's mood, dust tail shearing as radiation pressure sorts grains by size. As elongation grows, ground-based telescopes reclaim it at low altitude before dawn, first in wide-field survey passes, then in targeted pointings. Mid-sized telescopes deliver photometry and gas bands if activity lingers. Large apertures step in as the continuum fades, carving out narrowband detections and polarimetry, while the tail's contrast still cooperates. Space observatories, If scheduled, drop in for deep chemistry or inner coma structure, while the signal-to-noise ratio still punches above 0. Eventually, everyone yields to the sky background and the tug of other targets. The comet doesn't stop. Our instruments just stop being invited to the signal. The tail architecture unspools on its own timetable. Ion features fade first as photoionization slows and mass loading dwindles. The plasma lance narrows, then dissolves into invisibility, unless a solar wind disturbance sweeps through to briefly gild it. Dust lingers. Large, low beta grains refuse to be pushed hard and sketch a pale fan that gradually leans toward the orbit behind the nucleus. Outbursts leave fossil curves, synchrons that betray past fireworks long after the engine goes quiet. A tenuous dust trail may persist for months, but with this geometry, it is a paintbrush stroke in a very large gallery. Because the orbit doesn't cross Earth's path, no meteoroid stream welcomes us later. There's no future meteor shower with this object's name on it. Not every comet writes poetry in our atmosphere. Some keep their diary to themselves. As activity wanes, the orbit solution grows calmer. Early non-gravitational pushes from jets fade with the sublimation, and the fit slides toward a clean two-body description with tiny, well-behaved corrections. The same cadence of astrometry that once nudged perihelion times by minutes now just polishes the outbound asymptote. Ephemeris uncertainty narrows fastest along track. Cross-track and radial components shrink as well, but the practical outcome is simple. Pointing becomes easy just as there's less left to see. That's observational irony. By the time you can aim perfectly, you're mostly measuring the absence of light. Detection thresholds draw the last line. Surveys with modest apertures bow out once the comet slips past their limiting magnitudes. Dedicated imagers extend the run by stacking, aligning on the non-sidereal motion so the nucleus stays sharp while stars streak. Deep stack strategies earn an extra magnitude or two. Narrowband tricks can claw back a gas detection if a parent molecule refuses to quit. The final entries in the logbook often come from big mirrors under excellent skies, hour-long stacks, careful sky flats, and photometry at the edge of systematics. After that, confusion noise and sky gradients bury the target. There is no bell, just a quiet consensus that further photons are more hope than signal. The nucleus leaves changed. Perihelion carves, sinters, and rearranges. A few vents collapse, a few new ones open, and the spin state may be tweaked by months of torque. A thin shell of fallback dust can armor formerly fresh patches, while sputtering in deep space resumes its slow edit the moment sunlight slackens. The chemistry we measured becomes history. The weathering clock restarts. Given enough time, cosmic rays will darken and toughen the skin again, pores will clog, and the next star it passes will face the same late but lively ignition curve we watched. Deep space doesn't do epilogues, it does cycles. There's a human timeline to the exit too. Data pipelines continue to re-reduce outbound images, merge multi-band photometry, and zero in on final production rates. Error bars tighten in the archival record. Models absorb the last points and retire their Monte Carlo clones. Conference talks pivot from what will we see to what did we learn, and preprints trade adjectives for uncertainties and caveats. The comet recedes into the literature the way it recedes into the dark, steadily, without drama, leaving plots instead of footprints. Space is vast. The hard part is not losing the thread when the sky stops sparkling. In the end, the fate is as simple as the definition. 3IATLAS departs unbound, joins the thin disk traffic, and resumes being a quiet traveler between suns. Its surface reset by one close pass, its interior still hoarding a chemical history from another nursery. We close the shutter, it keeps going. Next, we'll ask why this was only the third such visitor we've spotted, and how better sky coverage and smarter pipelines will turn rare postcards into a regular mail route. You find more guests after you install a better doorbell. Interstellar visitors aren't rare because the galaxy forgot our address. We've just been hard of hearing. A handful of very terrestrial constraints: where we look, how often, how deep, and what our software thinks is weird enough to keep. Filter the sky so aggressively that only a few travelers slip through. 3IATLAS made it. Many of its cousins didn't even ring our chime. Start with geometry's worst-kept secret. Most newcomers approach from small solar elongations, hugging the twilight. That sliver of sky is astronomers' Bermuda Triangle. Short windows, bright air glow, brutal gradients, and a sun you really don't want in the optics. Classic surveys prefer the comfy, dark, high elongation, high altitude, long exposures. Result: we are systematically deaf to fast inbound objects that appear first in evening or morning glow. Dedicated twilight programs help, but they fight physics with a headlamp and a caffeine budget. Depth is the second gate. A single visit limit of, say, magnitude 22 sounds impressive, until you remember that brightness falls off with both distance from the sun, less light to scatter, and distance from Earth, photons spreading out. Interstellar objects are small and far. Many never crest the detection horizon before or after their brief bright phase. Push the limit one magnitude deeper, and your searchable volume balloons, roughly a factor of 2-3 for uniform populations. 2 magnitudes, now you're in find a lot more of them territory. Malmquist bias then shows up at the party with a name tag. We preferentially detect the largest, dustiest, or most fortuitously lit visitors, and miss the legions of quieter ones. Cadence is the third rail. Surveys stitch tracklets from back-to-back exposures, separated by minutes to hours, then link those across nights. Move too slowly and you look like a star. Move too fast and you turn into a streak, bleeding signal across pixels until the detection algorithm shrugs. Many pipelines cut on an allowed rate of motion window to avoid being swamped by satellites and airplanes. Genuine hyperbolic speedsters can land outside that comfort zone. Trailing losses also demolish signal to noise, so a rock you could have seen as a point source becomes a probably nothing dash. It's not that the sky hid it, our settings did. Sky texture, piles on, dense star fields near the Milky Way, dilute sensitivity through confusion. The moon raises the sky floor, weather carves holes in nightly coverage, and hemispheric asymmetries leave seasonal blind spots. Even with multiple facilities, the global network still resembles a patchwork quilt, not a seamless blanket. Add the very human reality of triage. Analysts must sift thousands of candidates nightly, and you get a bias toward looks like known things, and against looks like a glitch, but might be history. Interstellar visitors often masquerade as both. Then there's the software's personality. Moving object pipelines are picky by necessity. They reject singletons, demand consistent motion vectors, and cross-check against catalogs of everything from asteroids to geostationary specks. False positives are cheap. Follow-up time is not. The conservative cuts that keep operations sane also prune genuinely oddballs. A hyperbolic trajectory looks only slightly off on night 1. Without rapid follow-up, its eccentricity stays within the noise and the object dissolves back into the sky. The moral: early follow-up is worth more than a heroic stack later. All these filters shape what interstellar means in our sample. We skew toward active visitors, the ones casting dust comely that boost their brightness, because inactive, rock-like bodies of the same size would be a magnitude or 3 fainter. That selection calls the roll. 2i Borisov and 3IATLAS look cometary. 1i Oumuamua was the minimalist outlier that squeaked in thanks to favorable geometry and a lucky network response. Until we push deeper and faster, the census will overrepresent the noisy guests and undercount the quiet ones. Enter the better doorbell. Wide field, high throughput surveys with deeper single visit limits and high cadence will expand the discovery volume dramatically. A facility that hits Young's 24/25th magnitude per visit over big swaths of sky every few nights doesn't just add incremental finds, it multiplies the number of accessible interstellar arcs. The difference between 22.0 and 24.5 in nightly depth is the difference between needing the comet to do you a favor and you doing the comet a favor. Faster alert streams and machine learning vettors, trained on streaks, trailed sources, and odd colors, will also rescue the candidates that legacy cuts would toss. Twilight-dedicated campaigns are the other upgrade. Short integrations, aggressive differencing, and tailored rate of motion filters aimed at the 5 to 50 root elongation band catch objects on their very first inbound appearances. Pair that with automated, same-night follow-up, robotic telescopes that can pivot within minutes, and you collapse orbit uncertainties before the trail goes cold. The goal is to convert maybe hyperbolic into definitely interstellar, while the media cycle is still brewing its first pot of coffee. Space-based assets will shift the bias too. Infrared surveyors avoid albedo traps. Dark objects glow thermally, even when they sulk in visible light, and they can stare at elongations that cook ground-based optics. That combination pulls in smaller, darker, and less active bodies, rounding out a sample currently dominated by ones willing to shed dust. The moment we remove must be bright invisible from the checklist, the population statistics will stop pretending dust equals destiny. Even with better hardware, the sociology of discovery matters. Alert brokers that cross-pollinate, survey, to follow up to spectroscopy, to orbit fit and back turn a faint blip into a secured track in hours. Open, machine-readable candidate streams let amateurs with serious gear dogpile immediately, adding time baseline from longitude to longitude. And smarter simulation campaigns can precede what we're looking for. Inject fake interstellar objects into real survey data to measure recovery efficiency, then tune cuts until you're missing only what physics actually hides. So why only the third? Because our system has been optimized for near-Earth rocks, main belt churn, and spectacular comets, not stealthy hyperbolic specks sliding through twilight at inconvenient speeds. Change the optimization target, and the count will climb. Within a few years of next generation, deep, high-cadence surveys hitting stride, and with twilight and infrared help, the background hum of candidate interstellar pings should become normal. Rarer than asteroids, sure, but no longer unicorns. And that's the happy ending. The universe didn't just start sending visitors. We started learning how to notice. Next, we'll wrap the series by stepping back to the big picture. Why 3IATLAS matters beyond the headlines. How a single alien snowball recalibrates our models. And what to watch as the data keep refining the story. Science, changing the universe one weird rock at a time. A single interstellar comet seems like a curiosity, a postcard with no return address, but it punches far above its pixel count. When a foreign ice ball threads our skies, it becomes a calibration source for 3 sprawling stories at once. What comets are made of, how planetary systems grow and shed debris, and how often the galaxy tosses us souvenirs. None of those are trivia. They're the scaffolding we use to explain why planets end up where they do, and what ingredients they inherit. Start with chemistry. Planet formation models draw snow lines on a protoplanetary disk, like isotherms on a weather map. Where different ices condense, you get distinctive volatile ratios frozen into pebbles, CO and CO2 out in the deep freeze, water closer in, organics and nitriles sprinkled by grain surface chemistry and UV processing. When an interstellar comet vents, it converts those old lines on a theorist's whiteboard into measurable numbers. Relative abundances of CO2, CO, water, and simple organics act like thermometers and barometers for the nursery it came from. If those ratios cluster with values seen in our own comets, we learn that disk chemistry converges on common recipes around many stars. If they sit off to one side, we gain permission to diversify the menu. Colder kitchens, more aggressive UV, different grain growth timescales. Short version, The coma is a tasting menu for planet formation climates, and 3IATLAS adds a course we didn't cook. The mineral side matters just as much. Mid-infrared silicate features, grain porosity inferred from polarimetry, and thermal slopes tell us whether a disk ferried crystalline material from its hot inner regions into the cold outskirts where ice balls assemble. That's a yes-no vote on radial mixing mechanisms, turbulent diffusion, disk winds, vortices that our models depend on to move building blocks around. Crystals in a cold comet whisper, the conveyor belt was running. A mostly amorphous mix says the belt stalled, or it never existed. Either outcome is a constraint, and constraints are what let us prune pretty theories into durable ones. Now zoom out to dynamics. Ejection is a byproduct of planetary adolescence. Growing giants kick, resonances pump, binaries play gravitational ping-pong. The presence of 3IATLAS et al., together with its speed and approach direction, updates the league table of ejection environments. With each visitor, we refine the background traffic model, how many objects per cubic AU roam the local interstellar neighborhood, and that, in turn, feeds back into estimates of how common giant planets and tight binaries must be to seed such traffic. Think of it as planetary sociology inferred from wandering citizens. Interstellar doesn't mean exotic, it means statistically useful. Statistics is the third rail, and it's finally live. With a sample size of 3, you resist big conclusions, but you can do honest Bayesian updates. Detection rates folded through survey depth, sky coverage, and cadence translate into a posterior on the space density of interstellar bodies. Add composition buckets, quiet pebbles versus dusty ice balls, and you start to see category ratios instead of anecdotes. Each new detection narrows uncertainties like a vice. The delightfully unromantic punchline, one more interstellar discovery, can shift ejection rate estimates by factors, not percents, because the denominator is still small. A rare field where n equals 4 will genuinely change the conversation. There's also the laboratory value. Near the sun, an interstellar coma becomes a wind tunnel for charged particle physics and dust dynamics. At compositions our instruments haven't rehearsed. Fresh ions mass load the solar wind. Magnetic field lines drape and reconnect. Dust tails sort by size under radiation pressure, all in geometries we don't get to order ahead. Every ripple in an ion tail, every kink during a solar wind sector boundary crossing, is a free plasma experiment with boundary conditions we can measure. It's not just pretty, it's diagnostic. Methodologically, 3IATLAS is a rehearsal for doing this right, repeatedly, coordinated follow-up across wavelengths, rapid ephemeris updates with transparent uncertainties, and the habit of publishing upper limits, not just hero detections, sharpen the community's reflexes. That culture shift matters because future surveys will raise the tempo. Candidate Interstellar will go from headline to weekly tag, and the skill will be triage. Which targets get chemistry time, which get plasma time, which get deep dust work, and which justify a scramble by the biggest mirrors. Triage is unglamorous. It's also how you turn scarce hours into reliable science. There's a quieter payoff for planetary defense and small body studies, a network that can spot, classify, and characterize a hyperbolic faint fuzzball on awkward geometry is also a network that can respond to sudden outbursts, fragmentations, or odd near-Earth newcomers. Infrastructure is promiscuous. It serves whatever the sky throws. Build a better interstellar playbook, and you inherit a sturdier response to everything else. What to watch as the data keep arriving? First, the volatile ratios across time. Does the balance of CO2, CO, and water evolve in a way that screams layered nucleus, with different regions waking up as the sun warms different latitudes? Second, grain diagnostics. Do polarimetry and thermal spectra suggest fluffy aggregates or compact chips? And do those properties change after perihelion as the surface is reworked? Third, any isotopic footholds, even upper limits. A DH or Piral 15N nudge outside solar system norms would ripple through origin stories for comets and, by extension, for volatile delivery to young worlds. Fourth, non-gravitational nudges and spin state clues. If jets noticeably torque the nucleus, we learn how vents are arranged and whether the surface behaves like a cohesive crust or a loosely bound rind. Fifth, the outbound fade rate. How fast activity collapses after closest approach is a fingerprint of permeability and mantle thickness forged by long interstellar weathering. Finally, expect surprises. Space routinely violates our narrative pacing. Maybe a late outburst opens a chemistry time capsule. Maybe the ion tail stages an extravagant disconnection during a solar tantrum. Maybe the nucleus proves small, tough, and maddeningly efficient, minimal mass, maximal lesson. The value isn't in predicting plot twists, it's in wiring the instruments and the analysis pipelines so that, when the twist arrives, it turns into numbers instead of anecdotes. Curiosity is great. Calibration is greater. Taken together, 3IATLAS is a bridge. It ties dust physics to disk models, volatile ratios to snowline maps, encounter rates to planetary demographics, and instrument readiness to a future where interstellar visitors are rare but routine. The sky just added a new data stream. Our job is to turn it into knowledge without getting high on our own headlines. One weird rock at a time is plenty. Next, as a capstone, we can assemble a compact field guide to interstellar visitors, checklists for observers, decision trees for follow-up, and a pocket index of spectral lines. So the next arrival meets a community that's ready, patient, and pleasantly unsurprised.